On the telegraph line running between Boston and Portland, Maine, two operators notice something they cannot explain. Messages are moving cleanly across the wire, and neither man has touched the battery switch in minutes. One of them reaches down and disconnects the power source completely, just to see what happens. The signal keeps coming anyway. Somewhere above the line itself, unseen and unannounced, something else is now doing the sending, and neither operator has a word yet for what that something is. Not every telegraph office gets off that easy. Across offices in the northeastern United States and over in Europe, operators grab for switches that spit sparks into their palms, feel real shocks through their gloves, and watch paper tape curl, smoke, and in more than one recorded case, catch fire outright. No storm warning went out. Nothing on the schedule explained it. The copper wires strung between cities have simply, for reasons nobody working that night understands, become live on their own. The morning before, in a private observatory in Red Hill, England, an amateur astronomer named Richard Carrington is doing what he does most clear mornings, projecting the sun's image onto a screen and sketching the sunspots crawling across its face. At 18 minutes past 11, on the 1st of September, part of one sunspot group erupts into a blinding white light that holds for about 5 minutes. Carrington has just become the first person to witness a solar flare, though he has no framework yet for what he watched. He is not imagining it. A second astronomer working independently a few miles away, Richard Hodgson, records the same flash at the same minute, which rules out a smudge on a lens or a trick of tired eyes. Neither man understands yet that he has just watched the trigger get pulled on the most powerful geomagnetic storm ever recorded. The light itself took 8 minutes to reach their telescopes. The part of this that actually breaks things is still on its way. What Carrington and Hodgson saw flare on the sun's surface was a coronal mass ejection, something like 1 billion tons of magnetized plasma thrown outward at several million miles an hour. An eruption like that usually takes 3 or 4 days to cross the 93 million miles to Earth. This one arrives in roughly 17 hours. The best guess is that an earlier, smaller eruption had already cleared a path through the solar wind days before, and the second, bigger punch simply had an open road. When that wave of charged particles slams into Earth's magnetic field, it does not pass through quietly. It compresses the magnetosphere and rings it like a struck bell, inducing electrical current in anything long enough to behave like an antenna. Telegraph wires strung for hundreds of miles, pole to pole, across 2 continents, turn out to be excellent antennas. Nobody built them to be. Nobody knew, in 1859, that such a thing was even possible. The visible signature of it all was the aurora, and on the night of September 1st, it did something it essentially never does. It showed up everywhere. Skies burned red and green over Havana, over the Hawaiian Islands, over Colombia, barely 10 degrees north of the equator, a latitude that has no business hosting the northern lights. In parts of the northeastern United States, newspapers later reported people reading fine print outdoors after midnight, lit by nothing but the sky. In the Rocky Mountains, gold miners camped at high altitude woke in the middle of the night convinced morning had arrived. Some started cooking breakfast. Some saddled horses and began the day's work hours early, working by the glow of the aurora alone, certain the sun itself was already up. It must have been disorienting to be that confident about the time and have the sky itself be the thing lying to you. One of the clearer first-hand accounts comes from a Boston operator named Frederick Royce, who later described unplugging his line's battery entirely and continuing to send working messages to a colleague in Portland, powered by nothing but the current the storm itself was inducing in the wire. For roughly 2 hours, the two men held a real conversation, running on a magnetic disturbance happening somewhere above their heads. Royce called it the strangest thing he had seen in years on the job, and he was not exaggerating. At the Kew Observatory outside London, the instruments built to track Earth's magnetic field simply gave up trying to keep pace. The magnetometers recording pins, designed to trace slow, gentle daily variation, were driven so far and so fast off their normal range that the ink ran clean off the edge of the paper. The device meant to measure the storm could not physically capture how large the storm actually was. 1859 sat near the peak of the sun's roughly 11-year cycle of activity, a rhythm scientists had only just started to notice, thanks largely to a German pharmacist turned amateur astronomer named Heinrich Schwab, who spent decades quietly counting sunspots from his own backyard. Carrington's flare fit a pattern nobody yet had proper language for, an ordinary star going through an entirely ordinary mood swing, violent enough to reach 93 million miles and touch a telegraph key in Maine. Sit with how little infrastructure actually existed to break. In 1859, the telegraph was close to the only long-distance electrical network humanity had ever built. No power grid yet, no satellites, no pipelines carrying current across hundreds of miles. And that one thin, young network still caught fire in places, shocked its own operators, and briefly went haywire across 2 continents at once. The storm did not need much to work with. It simply does not have less to work with now. Jump ahead to March 1989. A storm nowhere near Carrington's strength induces enough current in a single Hydro-Quebec transmission line to trip protective relays and collapse the entire provincial power grid in about 90 seconds. 6 million people lose power in the middle of a Canadian winter. That storm barely registers as a footnote next to what happened in 1859, and it still took a modern grid down in under 2 minutes. Then there's July 2012, the storm almost nobody has heard of because it never actually hit us. A coronal mass ejection erupted from the sun with strength researchers later compared directly to Carrington's storm, crossing a path that would have intersected Earth's orbit, except Earth simply was not standing there yet. The planet missed the strike by roughly 9 days of orbital position. 9 days is the entire margin between an ordinary year and a global blackout. Physicist Daniel Baker at the University of Colorado led the team that studied the 2012 event afterward, running the numbers on what a direct hit would have actually cost. Their estimate for the United States alone landed somewhere around $2 trillion in the first year, with full recovery stretching anywhere from 4 to 10 years. $2 trillion is not a hypothetical figure anymore. It is what nearly happened, missed by little more than a week. Modern civilization runs on exactly the kind of long, grounded conductor a geomagnetic storm loves most. High-voltage transmission lines strung across entire continents, feeding into transformers the size of a small house. Those transformers were never built to absorb the direct current a Carrington-class storm induces. Push one past its tolerance, and it does not simply trip offline. In the worst cases, it melts internally, permanently, with no reset switch to flip afterward. Replacing one of those transformers is not simple, either. Many are custom-built, some manufactured overseas, and a single unit could take a year or more to design and deliver even under ordinary circumstances. Lose several dozen of them at once, across an entire continent, in the same geomagnetic event, and the replacement timeline stretches into years, not weeks, while whole regions wait in the dark for parts that do not exist yet. None of that accounts for what simply did not exist in 1859. A sky full of satellites handling communication, navigation, and weather forecasting, all sitting directly exposed to the same charged particles and radiation a storm like this throws outward. GPS timing signals, the kind that quietly synchronize banking transactions and cellular networks, are vulnerable too. In 1859, the wires caught fire. Today, the list of things that could fail runs considerably longer, and most of it stays invisible until the moment it stops working. Airlines already reroute flights away from the poles during serious solar storms, because high-frequency radio communication and GPS accuracy both degrade near the poles when the particles arrive, and pilots flying those routes lose tools they depend on to know exactly where they are. That is a precaution airlines already take for storms considerably weaker than the one that hit in 1859. It is a small, quiet admission of how exposed the whole system still is. Modern satellites can watch a coronal mass ejection, leave the sun, and estimate roughly when it will arrive. Sometimes with almost a full day of notice, sometimes with as little as 15 minutes if the geometry is unlucky. A day sounds like plenty until you consider what that time actually has to cover. Powering down sections of a continental grid, grounding satellite operations, warning every airline currently in the sky, all inside a window that might close before the paperwork even clears. Researchers who study the historical record of solar storms estimate a Carrington-class event hits Earth roughly once every 100 to 200 years, which puts the current weight, counted from 1859, well inside the range where the next one could arrive at any point, with no particular warning attached to the calendar. Not a certainty on any fixed date, just a probability that keeps climbing with every year nobody spends preparing for it. Space weather forecasters today still use the 1859 storm as their reference point for the very top of the scale, Category G5 on the 5-step system used to grade geomagnetic disturbance. Every extreme storm since gets measured against a benchmark set by a man sketching sunspots through a small telescope in his own backyard. A man who had no idea he was about to hand every future forecaster their unit of comparison. Nobody in 1859 called what happened an attack, because nobody yet understood there was anything to attack. The sun is the entire reason there is a solar system worth naming. The reason Earth holds water and warmth and breathable air at all. It is also, on its own unpredictable schedule, capable of reaching across 93 million miles of empty space and setting a telegraph office on fire. Both of those facts are true about the same star, at the same time, and neither one cancels the other out. By the 3rd of September, the aurora had faded, the telegraph lines had cooled, and most of the world went back to treating the sun the way it always had, as a fixed, dependable point in the sky, harmless by default. It was never actually any of those things. For 1 week in September, it simply showed a fraction of what it is capable of to a species that had only just learned how to wire two cities together. At the bottom of a crater near Mercury's North Pole, the temperature never rises above roughly minus 170 degrees Celsius. Not once, not for a single hour, in the entire history of the solar system. Overhead, less than a couple hundred miles away, the ground is hot enough to melt lead. Both of these facts describe the exact same planet, orbiting the exact same star at the exact same moment. Mercury is the innermost planet in the solar system, barely larger than Earth's own moon, close enough to the sun that from its surface the sun appears roughly 3 times larger and far brighter than it does from Earth. It is a small, gray, heavily cratered world, and for most of history it was the planet astronomers understood least, mostly because it never strays far enough from the sun's glare to get a clean, long look. Long before Messenger, NASA's Mariner 10 became the first spacecraft to ever visit Mercury, flying past 3 times between 1974 and 1975 using a clever gravitational slingshot off Venus to keep looping back. Its cameras mapped only about 45% of the surface, limited by the timing of each flyby and the same sunlight that makes the planet so brutal to study from Earth. Mercury kept the rest of its face hidden for another 3 decades. By day, Mercury's surface bakes past 430 degrees Celsius, hot enough to melt lead, hot enough that no land or humanity has ever built could survive sitting on that ground for long. That heat is not surprising on its own. Mercury orbits, on average, about 36 million miles from the sun, closer than any other planet manages to stay. What is strange is what happens after dark. Mercury has essentially no real atmosphere. Just a thin, wispy exosphere too sparse to trap or move heat around the planet. So as soon as the sun sets, the ground simply radiates its warmth away into space with nothing to stop it. Nighttime temperatures fall to roughly minus 180 degrees Celsius. On a single planet, in a single rotation, the temperature swings by more than 600 degrees. For decades, astronomers assumed Mercury was tidally locked to the sun the same way the moon is locked to Earth. one face permanently cooking, the other permanently frozen, based on early telescopic maps drawn by the Italian astronomer Giovanni Schiaparelli. Then in 1965, radio astronomers pointed a radar dish at Mercury and clocked its actual rotation. The planet was not locked at all. It was spinning on its own strange rhythm, one nobody had predicted. That rhythm turns out to be a 3-to-2 spin orbit resonance. Mercury completes exactly 3 full rotations on its axis for every 2 trips it makes around the Sun. It is a gravitational lock, but a looser, stranger one than a simple tidal freeze, likely settled in a place billions of years ago because of Mercury's unusually elongated, eccentric orbit. Nothing about it is arbitrary. It is just not the tidy answer anyone expected. Do the math on that resonance, and something strange falls out the other end. Because Mercury spins 3 times for every 2 orbits, a single solar day there, sunrise to sunrise, works out to about 176 Earth days, which is 2 full Mercury years. Spend 1 day standing on Mercury's surface, and by the time the Sun sets again, you will have watched the planet orbit the Sun twice over. There is an even stranger side effect. At certain points along Mercury's orbit, its unusual speed combined with its slow spin means the Sun, as seen from the surface, briefly appears to stop, reverse direction, and set back the way it came before continuing on its original path. Observers call it the double sunrise. It is not a glitch. It is just what happens when a planet's spin and its orbit stop agreeing with each other the ordinary way. None of that is Mercury's strangest feature. Crack the planet open, at least on paper, and the geometry inside makes even less sense than the sky above it. Mercury's iron core takes up something like 85% of the planet's entire radius. On Earth, the equivalent core would have to reach almost out to the crust. On Mercury, it very nearly does. For comparison, Earth's core, large as it is, only accounts for around half the planet's radius, with a thick mantle of rock wrapped around it. Mercury barely has a mantle at all by comparison, just a thin shell of rock draped over a metal heart that dominates almost the entire interior. Something happened to this planet early on that stripped away most of what should have been there. The leading explanation is violent. Sometime in the solar system's first few 100 million years, something big, possibly a planetesimal, a meaningful fraction of Mercury's own size, slammed into it at enormous speed, blasting away most of the outer rocky layers and leaving the dense metal core largely intact underneath. What we see today may simply be the leftover core of a planet that used to be considerably bigger. Not every researcher is fully convinced. Some argue the Sun itself, in its violent youth, could have vaporized and blown away Mercury's outer layers before it ever finished forming. Either explanation lands in the same place. Mercury, as it exists now, looks like a planet with a piece missing, and every leading theory for why involves something catastrophic happening extremely early and extremely close to the Sun. Keep that idea in your back pocket, because this will not be the last time in this story that a giant planet-reshaping collision leaves something behind rather than simply erasing it. Violence in this solar system has a habit of surviving its own aftermath, whether it is a stripped-down core or something considerably closer to home. Now go back to the poles, because this is where Mercury stops making sense in the other direction entirely. In 1991, astronomers pointed the radar dish at Arecibo in Puerto Rico at Mercury and picked up something odd bouncing back from the polar regions. Bright radar reflections, the exact kind of signature ice produces, coming from the single hottest planet in the inner solar system. The reason is almost embarrassingly simple once you know it. Mercury's axis is tilted by barely 2 degrees, almost perfectly upright relative to its orbit. That means sunlight never reaches the floors of certain craters sitting near the poles, no matter what time of year it is, no matter how the planet is currently facing the Sun. Some of those crater floors have not seen direct sunlight in longer than anyone can meaningfully calculate. The radar hint sat there for 2 decades until NASA's Messenger spacecraft arrived in orbit around Mercury in 2011, the first mission ever to actually circle the planet rather than just fly past it. Its instruments picked up hydrogen signatures and imaged crater floors consistent in every way that mattered, with frozen water sitting exactly where the radar had suggested it would be, undisturbed, long before anyone confirmed it existed. Estimates for how much ice is actually sitting inside those shadows run into the hundreds of billions of tons, maybe more, layered inside craters with names like Chowmeng, Fu, and Prokofiev, tucked at the planet's poles like something hidden on purpose. It is not a thin frost, either. In places, the deposits appear to run many meters deep, buried under a thin layer of dark, insulating material that may be helping keep it cold enough to survive. Mercury's craters carry an unusually artistic naming scheme, each one named after a painter, composer, author, or other creative figure from history: Rembrandt, Beethoven, Tolstoy, Dostoevsky. It is a strange kind of memorial, a roll call of human imagination scattered across the surface of the one planet in the solar system least hospitable to imagining anything comfortable happening there at all. Nobody thinks that ice formed on Mercury. The leading idea is that comets and water-rich asteroids have been slamming into the planet for billions of years, the same way they struck every other world in the young solar system. And a small fraction of the water thrown loose by each impact happened to drift into a permanently shadowed crater and simply never leave again. A cosmic accident, repeated often enough, adds up to a genuine reserve. So picture plainly, a planet that spends its days hot enough to melt lead is quietly holding onto reserves of frozen water inside craters less than a couple hundred miles from that same furnace, untouched, unmelted for what could be billions of years. Mercury is not simply extreme. It is 2 opposite extremes at once, permanently, with almost nothing gentle in between them. That discovery ended up maturing well beyond Mercury itself. If ice could survive in permanent shadow on the hottest planet in the solar system, it forced scientists to take seriously the idea that other airless, sun-blasted worlds might be hiding the exact same thing. Sure enough, the moon's own polar craters later turn out to be hiding water ice too, tucked in a shadow using the identical trick. None of that makes Mercury hospitable or even remotely close to it. The ice sits at the poles precisely because nothing else about this planet is survivable, wedged into the only pocket of the entire world where the sun's rules briefly do not apply. It is less a resource waiting to be used, and more a reminder that even the most hostile place in the neighborhood still has a loophole tucked somewhere inside it. Mercury spends every day of its existence pinned between 2 extremes it never gets to escape: a surface hot enough to reshape metal, and craters cold enough to preserve ice since before complex life ever existed on Earth. Nothing about that arrangement resolves. It just sits there, both things at once, close enough to the sun that it should not be possible, and true anyway. For all its extremes, Mercury has one advantage almost no other planet nearby can claim. Nothing about its heat stays trapped. Whatever bakes the surface by day radiates straight back out into space by night, with no atmosphere thick enough to hold it in. There is another planet in this system that made the opposite mistake, and it is currently sitting under nearly 100 times Earth's air pressure because of it. Messenger itself did not survive Mercury either, though not because of the heat. After 4 years mapping the planet in more detail than any mission before it, the spacecraft ran out of fuel in 2015 and, with nothing left to correct its orbit, was allowed to fall. It struck Mercury's surface at roughly 8,000 miles an hour, adding one more crater to a planet that, by that point, had gotten very good at collecting them. October 22, 1975. A Soviet lander named Venera 9 touches down on the surface of Venus and immediately starts sending images back to Earth, grainy, black and white, showing flat volcanic rocks stretching out under a strange, filtered orange light. 53 minutes later, the signal stops. Not because of a malfunction anyone can pinpoint, because the planet itself has finally finished crushing and cooking the machine that dared to land on it. Venus is, on paper, the planet most like Earth in this entire solar system. Similar size, similar mass, similar rocky composition, formed from roughly the same disk of material at roughly the same time. Astronomers used to call it Earth's twin, back when that seemed like a reasonable, hopeful guess. Nothing about the surface underneath those clouds turned out to be hopeful at all. The surface of Venus sits at roughly 465 degrees Celsius, hot enough to melt lead outright, and hotter, on average, than Mercury. Despite Venus orbiting considerably farther from the Sun, layered on top of that heat is a surface pressure about 92 times what Earth feels at sea level, the equivalent of standing nearly a kilometer underwater in an ocean made of gas instead of water. None of that comes from proximity to the Sun alone. Venus's atmosphere is almost entirely carbon dioxide, thick enough and efficient enough at trapping heat that it triggered what scientists call a runaway greenhouse effect. Heat gets trapped, oceans evaporate, water vapor traps even more heat, and the cycle feeds itself until there's nowhere left for the extra energy to go except into the ground. Wrapped around all of it are clouds of sulfuric acid, drifting roughly 30 to 40 miles above the surface, dense enough to hide the ground from every camera pointed at Venus from orbit for most of the 20th century. From above, Venus looks calm, pale, almost gentle, a soft cream-colored marble hanging in the dark. Is lying. The first real confirmation of how bad it actually was down there came from Mariner 2, an American probe that flew past Venus in December 1962 and used a microwave radiometer to peer straight through the clouds. What it measured back was a surface radiating heat consistent with several hundred degrees, numbers that quietly ended any lingering hope Venus might be a warm, swampy, almost habitable place. The Soviet Union had already committed to Venus specifically, launching an entire program named Venera aimed at reaching the surface directly rather than just studying it from orbit. The first few attempts barely counted as attempts. Venera 1 lost contact on the way. Venera 3 became the first human-made object to strike another planet's surface in 1966, but systems failed during descent and it never sent back a single reading. Venera 4 got further, transmitting data as it descended by parachute through the atmosphere in 1967, right up until its instruments recorded pressure and heat readings far beyond anything its designers had planned for. The vessel was crushed before it ever reached the ground. Soviet engineers had built a spacecraft for the Venus they expected. Venus turned out to be considerably worse than the one anyone had modeled. Every failure fed directly into the next design. Engineers thickened the hull, switched to a titanium pressure vessel, and started pre-chilling the entire lander before descent, essentially freezing it in advance so it would have a few extra minutes before the heat outside caught up and cooked it from the inside out. Surviving Venus, it turned out, meant treating the descent itself as a race against a clock nobody could stop. To even test whether their landers could survive, Soviet engineers built pressure chambers on Earth capable of simulating Venus's crushing atmosphere, essentially recreating hell in a laboratory before ever launching a single spacecraft. Getting the simulation right took years of trial and error of its own, because nothing on Earth naturally reaches 92 atmospheres of pressure combined with temperatures hot enough to melt lead, not even at the deepest points of the ocean floor. That redesign paid off, barely, in December 1970. Venera 7 became the first spacecraft to transmit data from the surface of another planet, sending back roughly 23 minutes of readings after apparently tipping onto its side during landing. 23 minutes does not sound like much of a victory. After everything that came before it, it was practically a triumph. Venera 8 followed 2 years later, surviving around 50 minutes and returning enough data to start building a real picture of the ground itself. Dense basalt-like rock, roughly consistent with volcanic terrain, sitting under lighting engineers described as similar to an overcast day on Earth despite the blistering heat. Venus, it turned out, had a landscape too, buried under all that heat. When Venera 9 sent back its now famous 1975 photographs, the ground it showed was not what most scientists had expected. Sharp, angular slabs of rock, relatively unweathered, sitting in a landscape that looked almost freshly broken rather than worn smooth by billions of years of erosion. Whatever process shapes the surface of Venus, it does not appear to work slowly. The United States ran its own version of the same experiment in 1978, when NASA's Pioneer Venus mission dropped 4 separate probes through the atmosphere simultaneously. None of them were built to survive the surface at all, only the descent. One of them, against every design expectation, kept transmitting for nearly an hour after impact anyway, a small, accidental bonus data set nobody had actually planned for. The record for survival on Venus's surface belongs to Venera 13, which landed in March 1982 and kept transmitting for about 127 minutes, better than 2 hours, before the heat and pressure finally won. In that window, it managed something no lander before it had: color photographs of the surface and a drilled soil sample, analyzed right there on the ground before the machine doing the analysis was destroyed. None of the Venera landers died from one dramatic malfunction. They died from an environment offering no gentle way to fail: heat-softening seals, pressure-crushing housings, corrosive gas working in every gap in the hull at once, until some critical component simply stopped functioning under a combined assault no design on Earth could hold off indefinitely. The planet did not need a single flaw. It just needed time, and it never ran out of time. To date, no spacecraft from any nation has survived on the surface of Venus for longer than about 2 hours, and only a handful have survived that long at all. That is still the current record, decades later, not because nobody has tried to beat it, but because building something that can function even briefly under those conditions remains genuinely, seriously difficult. With direct surface exploration effectively closed off, NASA turned to radar instead. The Magellan spacecraft spent the early 1990s in orbit around Venus, mapping the surface underneath the clouds using radar rather than cameras, and it revealed a planet covered almost entirely in volcanic plains, with an estimated average surface age of somewhere between 300 and 500 million years. Young, on a planetary timescale, something resurfaced most of Venus relatively recently, and nobody fully agrees yet on what. Some climate models suggest Venus may have had liquid water on its surface for a stretch of its early history, possibly even an ocean, before the runaway greenhouse effect took hold and boiled it away for good. That idea is still debated, and the evidence is thin compared to what exists for Mars. But if it is true, Venus is not simply a planet that formed hostile. It may be a planet where Earth-like conditions failed first. Whatever Venus started as, what it became is the clearest demonstration in the entire solar system of what a greenhouse effect looks like, with absolutely nothing to stop it. Not a controlled process, not a manageable trend. A one-way door, closed from the far side, sealing in enough heat to render an entire planet's surface permanently unrecognizable to whatever it might have once been. Imagine being one of the engineers back in Soviet mission control, listening to a lander's signal come through clean, then start to degrade, then go silent, all inside less than 2 hours, every single time, across mission after mission spanning more than a decade. You build something as tough as materials science allows. You watch a whole planet take it apart anyway. That is not a mission failure. That is closer to a fair fight, lost. Space agencies have not given up on Venus, even with that track record sitting in the mission history books. NASA and the European Space Agency both have missions planned for the coming years, aiming to study the atmosphere and map the surface in far greater detail than Magellan ever managed. None of the current plans include sending another lander down to sit on the ground for long. That lesson, at least, appears to have been fully learned. Venus and Earth started from close to the same raw materials, at close to the same distance range from the same star, and ended up separated by roughly 465 degrees Celsius and 92 atmospheres of crushing difference. Something in the details, not the broad strokes, decided which planet got oceans and which one got a surface that destroys machines built specifically to survive it. That margin is thinner than most people assume. Earth avoided Venus's fate so far, and depending on which scientist you ask, the reasons range from simple orbital distance to a long list of quieter, more fragile, stabilizing factors that nobody fully understands yet. One of the biggest of those stabilizers is not even part of Earth originally. It was born out of violence 4.5 billion years ago and is still up there right now, doing its job. Venus adds one more strange detail on top of everything else. It rotates backward compared to almost every other planet in the solar system, and it does so unbelievably slowly, taking about 243 Earth days to complete a single spin. That is longer than Venus takes to orbit the Sun. A single day on Venus outlasts a single year on Venus, and nobody fully agrees on why its rotation ended up running in reverse in the first place. Every single Venera mission ends the same way in the historical record: a stream of readings, a handful of photographs, and then nothing permanently on a planet that has never once let a machine leave under its own power. Venus does not damage what lands on it. It finishes it, and it has been finishing everything sent its way for as long as anyone has been brave enough, or stubborn enough, to keep trying. Picture Earth as it existed about 4.5 billion years ago, barely formed, still glowing, its surface an ocean of molten rock rather than water. Into that world slams an object roughly the size of Mars, a rogue protoplanet astronomers later named Theia, striking at an angle rather than head-on, hard enough to liquefy what was already barely solid. Within hours, a significant fraction of both worlds is no longer where it used to be. Theia takes its name from a Titan in Greek mythology, mother of Selene, the goddess who personified the moon itself. Whoever chose that name for a hypothetical planet nobody has ever seen direct evidence of clearly appreciated the irony. Mythology had already cast the moon's mother centuries before astronomers worked out that the moon's actual origin involved a violent collision with a world that might as well share her name. That collision is the leading explanation astronomers have for where the moon actually came from, known as the giant impact hypothesis. It was proposed in the 1970s by planetary scientists William Hartmann and Donald Davis, refined further by Alastair Cameron and William Ward in decades of subsequent evidence. Chemical, orbital, and geological have only strengthened the case rather than weakened it. The impact itself likely threw an enormous volume of vaporized and molten rock, torn from the mantles of both Earth and Theia, into orbit around the wounded planet. That debris did not linger as a formless ring for long. Models suggest it accreted into a single body, the moon, in as little as a century, an almost absurdly fast construction project for something that would go on to last billions of years. The strongest evidence for this violent origin came from the Apollo missions themselves, and specifically from the rocks the astronauts carried home. Lunar samples share oxygen isotope ratios nearly identical to Earth's own, a chemical fingerprint that essentially rules out the moon forming somewhere else in the solar system and later getting captured. Whatever the moon is made of, it is made largely out of Earth. That similarity actually creates a puzzle of its own. Early simulations of the impact predicted the moon should be built mostly from Theia's material, not Earth's, yet the isotopic evidence leans overwhelmingly toward Earth. Researchers have spent decades adjusting the models, testing different impact angles and speeds, trying to explain why the moon looks so much like a piece of Earth instead of a piece of the object that hit it. It remains one of the field's more stubborn open questions. Some researchers now suspect Theia never fully left. A study published in 2023 proposed that two enormous, dense structures sitting deep inside Earth's mantle, first detected decades ago through seismic waves, and known as large low shear velocity provinces, might actually be surviving chunks of Theia itself, buried since the impact and never fully mixed into the rest of the planet. If that holds up, part of the object that created the moon may still be sitting underneath your feet right now. Whatever its exact recipe, the newborn moon started out entirely molten, a small world wrapped in its own ocean of liquid rock. As that magma slowly cooled and crystallized over millions of years, lighter minerals floated toward the surface while denser materials sank, eventually hardening into the pale, cratered highland crust that still makes up much of the moon's visible face today. In those earliest years, the moon sat drastically closer to Earth than it does now. Some estimates put the distance at only around 14,000 miles, compared to roughly 238,000 today. From Earth's surface, a moon that close would have filled a shocking portion of the sky, dragging brutal tides across whatever molten or newly solidified ground existed at the time. Over time, Earth's gravity did to the moon what gravity tends to do to close, lingering companions. It locked its rotation to match its orbit, a process called tidal locking. The moon still spins on its axis, but it spins at exactly the same rate it orbits Earth, which means the same hemisphere has faced us for essentially the entire history of complex life on this planet. That leaves an entire hemisphere of our closest neighbor that no human eye had ever seen directly until October 1959, when the Soviet probe Luna 3 swung around the moon and photographed its far side for the first time. The images were grainy, low resolution by any modern standard, and still genuinely historic. Humanity's first look at half of the object that has hung in our sky since before there were eyes to look up at it. The far side, once photographed, turned out to look meaningfully different from the familiar near side, heavily cratered, with far fewer of the dark, smooth basaltic plains called Maria that give the near side its recognizable face pattern. Explanations range from a thicker, far side crust that resisted ancient lava flooding, to a stranger idea still under real debate, that a second, smaller moon once existed, merged into the far side in a slow-motion collision of its own. Here is the detail that turns this origin story into something closer to a countdown. The moon is not staying put. It is drifting away from Earth at a measured rate of about 3.8 centimeters every year, roughly the speed a fingernail grows, tracked with extraordinary precision using mirrors astronauts left on the lunar surface during the Apollo missions. Observatories on Earth fire laser pulses at those mirrors, called retroreflectors, left behind by the crews of Apollo 11, 14, and 15, and time exactly how long the light takes to bounce back. That round trip currently takes a little over 2.5 seconds, and it has been getting very, very slightly longer year after year, ever since scientists started measuring it in the early 1970s. The mechanism behind that drift comes down to tides. Earth's oceans bulge slightly toward the moon, and because Earth spins faster than the moon orbits, that bulge gets dragged slightly ahead of the moon's actual position. The gravity of that lagging bulge tugs the moon forward, boosting into a very slightly higher, more distant orbit, while Earth's own rotation slows down in exchange, a fair trade of angular momentum that neither planet gets a say in. That exchange means Earth's days have been getting longer for the entire span of the planet's history. Not by much in any single human lifetime, but the pattern is unmistakable across deep time. Geological evidence preserved in ancient tidal sediment layers suggests days lasted only around 22 hours some 600 million years ago. Every single day on Earth right now is, technically, a little longer than the one before it. None of this would matter much if the moon were simply a passive rock in the sky. It is not. Its gravity plays an active role in holding Earth's axial tilt steady, the 23.5-degree lean responsible for seasons as we currently experience them. Research published by French astronomer Jacques Lascar and colleagues in 1993 modeled what happens to that tilt without a large stabilizing moon nearby, and the results were not reassuring. Without the moon's steadying pull, Lasker's models showed Earth's axial tilt could swing chaotically over millions of years, wandering anywhere from nearly 0 degrees to as much as 85, turning what are currently mild seasonal differences into climate extremes capable of reshaping entire ecosystems again and again, with no predictable rhythm at all. The moon is not decoration hanging in the sky. It is functionally load-bearing. There is something genuinely strange sitting inside that fact. The object currently responsible for keeping Earth's climate on something resembling a stable, predictable schedule was itself born from one of the most violent events this planet has ever experienced. A collision that came close to unmaking Earth entirely before it had the chance to become anything else. The thing protecting us and the thing that nearly destroyed us share the exact same origin story. The drift itself is not fast enough to threaten anyone alive today, or any generation reasonably close to today. 3.8 centimeters is nothing on a human timescale, but stretch that rate out across the deep future, and the moon's stabilizing influence weakens gradually as the distance grows, a slow unwinding of exactly the mechanism currently keeping Earth's climate as steady as it is. It is less an emergency than an inheritance quietly being spent down. For most of human history, people looked up at the same unchanging face of the moon and had no way of knowing it was hiding half of itself, let alone that it was quietly drifting farther away with every single orbit. It took spaceflight, actual hardware landed on actual lunar soil, to finally answer a question people had been staring at, without realizing they were even asking it, for the entire span of recorded history. Look up at the moon tonight, and you are looking at debris. Beautiful, load-bearing, life-sustaining debris, thrown loose from a wound Earth suffered 4.5 billion years ago, that happened to settle into exactly the orbit needed to keep this planet's climate survivable ever since. It is very hard to call that lucky. It is even harder to call it anything else. Humanity did not stop at photographing the far side either. In January 2019, China's Chang'e 4 mission achieved something no country had managed before, an actual, functioning landing on the moon's far side, requiring a relay satellite parked beyond the moon just to keep in contact with a hemisphere that never, under any circumstances, faces Earth directly. That relay requirement exists purely because of the tidal lock this chapter already covered. No signal sent straight from Earth can ever reach the far side directly. Not now, not in 1,000 years, not for as long as the moon keeps facing us with exactly the same patience it has kept since not long after the collision that made it. Every measurement humanity has taken of the moon, the isotopes in Apollo rock samples, the laser pulses bouncing off mirrors left in the dust, the far side images radioed home from probes decades apart, points to the same layered story. Something violent happened. Something stable grew out of it, and that stability, patiently, is already counting down toward its own slow ending, whether or not anyone down here is paying attention. Not every world in this solar system got a stabilizer like that. Mars, the next stop on this tour, never had a companion large enough to hold its tilt steady, and it lost something even more fundamental a long time ago. What that loss actually did to an entire planet is written across its surface in dry riverbeds that have not carried water in longer than anyone can comfortably imagine. Right now, a 6-wheeled rover is creeping across the floor of an ancient lake on Mars, alone, kicking up rust-colored dust that has not been disturbed by flowing water in roughly 3.5 billion years. It sends its findings back to Earth and waits, sometimes 20 minutes, just for the signal to arrive one way. Nothing answers except the silence the whole planet has been sitting in since long before anything on Earth grew a spine. That rover is driving across the wreckage of a genuinely different Mars. Roughly 4 billion years ago, this same planet had river channels carving through rock, lakes settling into low ground, and according to some of the more contested models, possibly enough water pooled in its northern lowlands to qualify as an actual ocean. Mars was never Earth, but for a while, it was considerably closer to Earth than it has any business being now. Orbiters have mapped the evidence in staggering detail. Branching river valleys, fan-shaped deltas spreading out exactly the way sediment spreads when it hits standing water, and dry lake beds ringed with terraces that look, from above, almost identical to shoreline features geologists study on Earth. Water did this. Water moving across a landscape for long enough to leave a signature that has survived billions of years of desert silence afterward. NASA's Perseverance rover landed in February 2021 inside Jezero crater, specifically because orbital images showed a textbook river delta fanning out across its floor, the unmistakable fingerprint of water flowing into a crater lake for a long enough stretch of time to build layered sediment fans. Perseverance did not land in a random spot. It landed inside what used to be a lakeshore. The rock itself backs up the pictures. Instruments on multiple rovers and orbiters have identified clay minerals and sulfate deposits scattered across ancient Martian terrain, minerals that, as far as anyone understands the chemistry, only form in the sustained presence of liquid water. Opportunity, another rover, spent years rolling past small spherical mineral deposits nicknamed blueberries, rich in hematite, another mineral with the same essential requirement: water and time. Curiosity, working a different site called Gale Crater since 2012, drilled into rock that turned out to be ancient lakebed mudstone, fine-grained sediment that could only have settled the way it did at the bottom of a calm, standing body of water. Inside that mudstone, Curiosity's instruments detected organic molecules, carbon-based compounds that are not proof of life on their own, but are exactly the kind of chemistry life would need available to work with. Nobody serious is calling that proof of ancient Martian life, and it is worth being precise about that, because organic molecules also form through purely non-biological chemistry, seeding meteorites, volcanic processes, chemical reactions that have nothing to do with anything alive. What it does prove is that early Mars had water, warmth, and the basic chemical ingredients sitting in the same place at the same time. Whether anything ever did something with that combination remains completely unknown. NASA's Viking landers touched down on Mars back in 1976, decades before Curiosity or Perseverance, and ran a series of biology experiments directly on Martian soil. One of them, the labeled release experiment, produced results that looked, on first read, suspiciously like a biological reaction. Scientists have argued about what actually happened in that soil sample for nearly 50 years now, and the argument still has not fully settled. So the real question is not really whether Mars once looked promising. The orbital images and the drilled rock samples settle that part fairly convincingly. The real question is what happened next, because whatever made early Mars wet and comparatively gentle is now sitting under a thin, cold, nearly airless sky, and the answer to that question starts not on the surface, but deep inside the planet's core. Earth's magnetic field comes from a dynamo effect deep in its core, a molten, electrically conductive outer layer churning and convecting as the planet slowly loses internal heat, generating a magnetic field strong enough to wrap the entire planet in an invisible shield. Mars almost certainly had the exact same kind of dynamo running once, powered by its own molten core, doing the exact same job for the exact same reasons. Mars simply lost that engine early. Being smaller than Earth, with roughly a tenth of its mass, Mars radiated its internal heat away considerably faster, and somewhere in a window scientists currently place between about 4.1 and 3.7 billion years ago, its core cooled enough that the internal churn driving its magnetic field slowed, faltered, and eventually stopped altogether. Mars also carries the scars of a considerably more active past written across its surface in stone. Olympus Mons, sitting in the Tharsis region, is the largest known volcano in the entire solar system, roughly 2.5 times the height of Mount Everest, built up over what was likely hundreds of millions of years of sustained volcanic activity that the planet today is no longer capable of sustaining. The evidence for that shutdown is written directly into the Martian crust. NASA's Mars Global Surveyor spacecraft, mapping the planet's magnetic field from orbit in the late 1990s, found faint, striped bands of magnetism frozen into the rock of the ancient southern highlands, a kind of magnetic fossil record left over from when the dynamo was still running. Younger terrain nearby shows nothing. The field simply stops appearing in the rock record, like a signal that got switched off partway through the recording. Losing a magnetic field sounds abstract until you understand what that field was actually doing. It was deflecting the solar wind, the constant stream of charged particles the sun throws outward in every direction before it can reach a planet's upper atmosphere directly. Earth's field still does exactly that every single day, invisibly, and mostly without anyone down here ever noticing the job is even happening. Without that deflection, the solar wind hits a planet's upper atmosphere directly, and it does not politely bounce off. Charged particles collide with atmospheric molecules, some of which pick up enough energy to simply escape the planet's gravity altogether, drifting off into space a little at a time, in a process that barely registers on any human timescale, but adds up to something enormous across hundreds of millions of years. NASA sent an orbiter named Maven to Mars specifically to measure this process directly, arriving in 2014. Its instruments confirmed the atmosphere is still being stripped away right now, actively, continuously, at a rate of roughly 100 grams of gas escaping into space every second. That is not ancient history. That is Mars today, still quietly losing what little air it has left. Maven even caught the process accelerating in real time. During a strong solar storm in 2015, the rate of atmospheric loss measured at Mars spiked dramatically, direct, immediate confirmation that the sun itself is the active agent doing the stripping, and that a planet without a magnetic field has no meaningful way to push back when the sun decides to push harder. Run that slow leak forward across hundreds of millions of years, and the math becomes brutal. Mars's atmosphere, once thick enough to support liquid water pooling on the surface, has thinned down to roughly 1% of Earth's atmosphere pressure today, composed mostly of carbon dioxide, too thin to hold meaningful heat, too thin to keep water from boiling away or freezing solid, depending on exactly where it sits. That thinning is directly why the rivers and lakes disappeared. Without enough atmospheric pressure holding things down, liquid water on the Martian surface today does not pool, does not flow the way it once did. It either freezes solid or boils away almost immediately, leaving water on modern Mars locked up mostly as ice, buried underground or sitting frozen at the poles, waiting in a form it can no longer safely leave. This is where Mars stops being simply a dead, red, distant curiosity and becomes something closer to a diagnostic tool. Planetary scientists call the practice of studying Mars alongside Earth and Venus comparative planetology, and Mars is, within that field, the clearest example anywhere in the solar system of what a habitable world looks like after its core stops protecting it. It is not a hypothetical. It is a completed case study, sitting right there, fully documented. Stand at the edge of Jezero crater, at least through a rover's cameras, and you're looking at more than a dry hole in red dirt. You are looking at what is left after a planet's internal engine quietly shuts off and stays off, at the multi-hundred-million-year aftermath of losing a magnetic field, laid out in plain geological view for anyone patient enough to read it. There is no restart button waiting to be found here, either. Mars's core, smaller and cooler than Earth's to begin with, is not expected to spontaneously reignite the kind of vigorous internal churn its dynamo once relied on. Whatever window Mars had for keeping its magnetic shield running appears to have closed permanently, sometime in its first billion years, and nothing observed since suggests that door is ever opening again. Earth's own core is still doing the job Mars's core gave up on billions of years ago, still churning, still generating the magnetic field that keeps the same solar wind from doing to this planet's atmosphere exactly what it did to Mars's. That core will not run forever either. It is simply, for now, still running, which is precisely the kind of quietly reassuring fact this entire film keeps circling back to test. Every planet covered so far in this tour carries some version of the same lesson. Whether it is a star capable of overwhelming a telegraph network in hours, a world boiling under its own trapped heat, a moon quietly drifting away from the planet it stabilizes. Mars simply shows what the ending actually looks like when one of those protections runs out completely, rather than merely threatening to. Perseverance is currently caching drilled rock samples in sealed tubes, left sitting on the Martian surface, waiting for a future mission, planned as a joint effort between NASA and the European Space Agency, to eventually retrieve them and bring them back to Earth. Whatever answer exists about ancient Martian life, if an answer exists at all, is most likely sitting inside one of those tubes right now, sealed, patient, further from home than any geological sample humanity has ever attempted to recover. For now, the rover keeps driving alone across ground that used to be a lake floor, sending data across a gap that takes light itself several minutes to cross, into a silence that has been sitting undisturbed since long before this planet lost the one thing that might have let it keep anything at all. Between Mars and Jupiter, there is a gap, and for a long stretch of the 1700s, astronomers could not leave it alone. The spacing of the planets seemed to follow a pattern, and that pattern insisted something belonged right there, some world of mathematics demanded, but no telescope had ever confirmed. So they went looking. What they eventually found in that gap was not a planet. It was a graveyard, and nobody had thought to ask what a graveyard was doing in the middle of a solar system. The suspicion is older than most people realize. Johannes Kepler noticed the strange jump in spacing between Mars and Jupiter as early as 1596 and said plainly that a planet was missing, sitting out there unfound, waiting on someone with better instruments. It took 2 more centuries before anyone had the tools or the patience to go looking properly. By 1800, a group of astronomers got organized about it, half jokingly calling themselves the Celestial Police, and started a coordinated hunt. They were beaten to it by a priest who was not even part of the search. On the first night of 1801, Giuseppe Piazzi, an astronomer working from an observatory in Palermo, noticed a faint point of light shifting position against the fixed stars over several nights. He named it Ceres, after the Sicilian goddess of harvest and grain. For a few triumphant months, it looked like the missing planet problem had been solved cleanly and for good. Then it got messy. Within a few years, astronomers found Pallas, then Juno, then Vesta, all circling in roughly that same gap. By the 1840s, the count had climbed past a dozen. By the end of that century, it was in the hundreds. Whatever was occupying that stretch of space was clearly not a single quiet planet minding its business. It was a crowd, and crowds are harder to explain than solitary objects. Today, the catalog runs past 1 million numbered objects, with automated survey telescopes adding more on every clear night, scanning the sky for anything that moves against the background stars. Most are unremarkable, tumbling rubble a few kilometers across, filed away, and mostly ignored. A small number get flagged, tracked, and quietly watched by people whose entire job is noticing when something out there changes its mind about where it is going. One of the early discoverers, a physician and astronomer named Heinrich Olbers, offered a dramatic explanation for all this leftover debris. A planet had once existed in that gap, he argued, and something had destroyed it, some ancient catastrophe scattering its remains along the wreckage of its old orbit. It is a wonderful story, violent, tidy, almost cinematic. It also happens to be wrong, as far as anyone today can tell. The real explanation is quieter and in its own way stranger. There was never a planet to destroy in the first place. Jupiter sits just beyond that gap, massive enough that its gravity kept stirring the material orbiting nearby into a constant simmer, speeding up every collision until rocks were smashing into each other too violently to ever stick together. Building a planet requires its raw material to merge gently. Jupiter made absolutely sure that never happened. So this is not a crime scene left behind by some ancient murder. It is a nursery that never managed to deliver. Picture bricks laid out for a house that kept getting knocked flat every time the walls started to rise, over and over for 4.5 billion years, until whatever was building it simply gave up. That is the asteroid belt, a construction site abandoned somewhere in the middle of the poor. Popular imagination pictures this place as a minefield, spacecraft weaving between tumbling boulders that nearly collide every few seconds. That image comes from movies, not from anything real. Stand on one asteroid, and the odds of spotting another with the naked eye are close to zero. The belt spans hundreds of millions of kilometers, and nearly all of that enormous volume is nothing at all, just cold, dark space stretched impossibly thin. Run the actual numbers, and the belt turns out to be more than 99.9% empty space. Add together every asteroid, every fragment, every speck of dust inside it, and the total comes to less than 4% of the mass of our own moon. Spread that little material across a region wide enough to swallow Mars, Jupiter, and everything between them, and you get something closer to a thin, patient fog than any kind of debris field worth fearing on sight. Ceres alone accounts for roughly a third of that total mass, which tells you how little competition it actually has out there. It is round, pulled into a sphere by its own gravity, which is why it eventually got reclassified as a dwarf planet rather than simply the largest rock in the neighborhood. NASA's Dawn spacecraft settled into orbit around it in 2015 and found something nobody expected: water ice and bright patches of salt that hinted at a slushy history hiding just under the surface. Get close enough to an asteroid, and it stops looking like the smooth gray stone from the textbook illustration. When NASA's OSIRIS-REx spacecraft visited a small asteroid called Bennu in 2018, it found a surface so loosely packed with boulders and dust that engineers compared the landing to touching down in a pit of plastic balls. Many asteroids are not solid rock at all. They are rubble piles, barely held together by their own weak gravity, never quite settled into being one single object. Vesta, the second largest resident of the belt, looks drier and considerably more violent. Its southern hemisphere is dominated by an impact basin so enormous it nearly split the object in two. Fragments blasted off Vesta during that ancient collision still fall to Earth today as meteorites, which means pieces of the asteroid belt have been quietly landing in fields and backyards for far longer than anyone was paying attention to notice. Jupiter's influence never really stopped managing the place. Map out the belt's orbits, and you find suspicious empty lanes running through it, called Kirkwood gaps, regions where an asteroid's orbital period falls into a clean mathematical ratio with Jupiter's own. Anything that wanders into one of those lanes gets tugged by the same gravitational rhythm again and again until its path turns unstable and it gets thrown clear. Jupiter is still landlord here, evicting tenants on a schedule nobody else can read. There's a second population entirely, tens of thousands of asteroids called Trojans, trapped not in the belt itself, but in stable pockets ahead of and behind Jupiter, held in place by the planet's gravity, the way leaves get caught in the eddies of a fast river. Jupiter has kept the gap between Mars and itself in permanent disorder, and it has been organizing loose debris across the entire solar system for 4.5 billion years without a single day off. Evicted is a polite word for what happens next. Some of the material thrown clear of those gaps drifts harmlessly off into deeper space, never bothering anyone again. Some of it gets redirected inward instead, toward the one part of the solar system that happens to be occupied by something that could actually care. That part of the solar system is where we live. Look at the moon through even a cheap backyard telescope, and you are reading a casualty report. Every pale scar up, there's an impact, a piece of debris arriving at tens of thousands of kilometers an hour with nothing to slow it down first. Mercury tells the same story. So does Mars, a planet that already lost its atmosphere and its magnetic field and has spent a few billion years since with no real shield left standing between its surface and the sky. Earth carries the same scars. We simply cannot see most of them anymore. Water, wind, plate tectonics and time erase impact craters here within a few million years, which sounds like a comforting cleanup crew until you think through what it actually implies. It means the bombardment never stopped. We just happen to live somewhere that quietly hides the evidence instead of preserving it. Small pieces of this debris hit Earth constantly, burning up harmlessly as the meteors you can watch on any clear night if you know where to point your patience. Something the size of a car arrives roughly once a year, usually over ocean or empty land, breaking apart high in the atmosphere before anyone on the ground even looks up. It is only the rare, large, slow-moving exception that turns the display from fireworks into an ending, and from the ground, in the moment, there is no way to tell which kind you are watching. 66 million years ago, something roughly 10 kilometers across left the belt, or somewhere very much like it, and began an unhurried fall toward the sun. Some estimates put the journey at over 1 million years from disturbance to arrival. Nobody on Earth felt it coming, because nobody on Earth had any way of watching for it, and there would have been almost nothing to do about it regardless. It struck near what is now the coast of Mexico, a peninsula called Yucatan, releasing energy equal to billions of nuclear weapons detonating at once. The impact set fire to an entire hemisphere, threw enough vaporized rock into the upper atmosphere to blot out sunlight for years, and ended the long reign of the dinosaurs. Not every dinosaur, technically. Birds survived, and by any honest classification, birds are still dinosaurs. But everything too large to fly, hide, or simply waited out underground was finished within a geological blink. That is not lost on the people who study this now. Space agencies keep growing lists of everything large enough to matter, run the orbital math decades ahead, and occasionally test whether we could actually do something about it. NASA's DART mission deliberately crashed a small spacecraft into an asteroid called Dimorphos in 2022, just to see whether a nudge early enough could change where a rock ends up years later. It worked, which is either deeply reassuring or a quiet admission of exactly how much attention this gap still deserves. So look again at that gap between Mars and Jupiter and try to hold both truths at once. It is not a crowded minefield, and it was never a wrecked planet's tombstone. Mostly, it is nothing, drifting in near total silence for millions of years at a stretch, doing no harm to anyone at all. And then, on a timescale far too long for any human institution to plan around, it is not nothing whatsoever. The belt does not need to be full to be dangerous. It only ever needed to be patient. So carry that thought forward, because this tour is about to visit the planet most responsible for the belt's condition in the first place. Jupiter never simply cleared that gap and moved on. It has stayed actively involved in the fate of everything nearby ever since. And its own neighborhood turns out to be even less forgiving than the graveyard it created. There's a storm on Jupiter bigger than the entire planet Earth, and it has been spinning without pause for at least 350 years. Nobody alive knows exactly when it started, because by the time telescopes were good enough to notice it clearly, it was already fully formed and already enormous. Astronomers in the 1600s might have caught its opening act. Nobody wrote down the date. It has just been raging quietly out there ever since, indifferent to whether anyone was watching. Galileo Galilei turned a telescope toward Jupiter in January of 1610 and found 4 small points of light orbiting it, proof that not everything in the heavens circled Earth. He never mentioned a red spot. Either it was not there yet, or his instrument simply was not strong enough to catch it. Either way, the storm that exists today may well be entirely younger than the 4 moons Galileo found orbiting the planet that same winter. Jupiter takes its name from the king of the Roman gods, ruler of the sky, a fitting choice for the largest object orbiting the sun after the sun itself. Ancient observers with nothing but naked eyes could see it was different, bright and steady and slow moving against the stars, and gave it the name of authority almost by instinct. They had no idea yet quite how much authority the name would turn out to fit. Jupiter itself does not do anything modestly. It is the largest planet in the solar system, more massive than every other planet combined, with over twice the mass of everything else orbiting the sun put together. And yet for all that bulk, it has no surface to speak of. No ground, no coastline, no place a lander could ever set down and simply sit still. It is a planet built almost entirely out of gas. Mostly hydrogen, with a healthy portion of helium, arranged in layers that get stranger the deeper you go. Near the cloud tops, it behaves the way you would expect gas to behave. Descend further, and the pressure climbs so high that hydrogen stops acting like a gas at all and starts behaving like a liquid metal, conducting electricity, churning in currents that likely generate the most powerful magnetic field of any planet in the solar system. So picture what actually happens if you try to fly a ship straight down into it. There is no crash because there is nothing solid to crash into. Instead, the atmosphere just keeps getting thicker and hotter and heavier around you. Pressure climbing without any final floor to stop it, until whatever you sent in gets crushed by the sheer weight of gas stacked overhead. Jupiter does not need a surface to kill something. It just needs depth. The storm itself, the Great Red Spot, was first described with any real confidence in the 1830s, when astronomers began keeping continuous records of it. Some historians think Giovanni Cassini may have spotted an earlier version of it back in 1665, a feature he called the permanent spot before it vanished from written record for a while and then reappeared. Whether it is the same storm reborn or a new one that inherited the same address is a question nobody can fully answer. For most of recorded history, the Great Red Spot was wide enough to fit 3 Earths across it side by side. It has been shrinking for well over a century now, and nobody is entirely certain why, though it remains, even diminished, comfortably larger than our entire planet. A storm system that could swallow Earth whole and still have room left over is not really a weather event anymore. It is closer to a permanent geological feature that simply happens to be made of gas. Some researchers who track its shrinking size wonder aloud whether the Great Red Spot could eventually break up entirely within a human lifetime or two, dissolving into smaller storms the way its cousins already have. Nobody knows for certain. It is a strange thought either way that something older than the United States, older than any continuous telescope record of it, might simply run out of momentum sometime in the coming decades, on our watch instead of some future generations. It is an anticyclone, a vast rotating high-pressure system with wind speeds along its outer edges measured at over 400 kilometers an hour. On Earth, a storm like this would eventually run into a coastline, a mountain range, friction from solid ground, something to slow it down and break its structure apart. Jupiter offers none of that. There is no land to make landfall on. The storm simply keeps going because nothing has ever given it a reason to stop. Jupiter finishes a full rotation in under 10 hours, the fastest spin of any planet in the solar system despite being by far the largest. That speed drags the atmosphere into powerful jet streams running east and west, banding the planet in the stripes visible through any decent backyard telescope. And it is exactly that violent spin that helps keep storms like the Great Red Spot organized and rotating instead of falling apart. Nobody has fully settled why it is red. The leading guesses involve chemical compounds, ammonia and phosphorus and sulfur among them, dredged up from deeper layers and altered by exposure to sunlight at the cloud tops. It is a strange thing to admit about the most photographed feature in the solar system after our own moon. We know its size, its wind speed, its rough age. We still cannot tell you with confidence why it is the color it is. It is not even Jupiter's only storm worth naming. There is a great cold spot in its upper atmosphere, discovered through infrared observation, and a chain of smaller storms nicknamed the String of Pearls, marching around a southern latitude in a loose, repeating procession. At the poles, NASA's Juno spacecraft found something nobody predicted: tight clusters of cyclones arranged in near-perfect geometric patterns, an octagon of storms circling the North Pole, a pentagon circling the South. All of that churning gas produces something else, something you cannot see in any photograph. Jupiter generates the strongest magnetic field of any planet in the solar system, roughly 20,000 times more powerful than Earth's. That field traps charged particles streaming off the Sun and off Jupiter's own volcanic moon Io, accelerating them into belts of radiation that dwarf anything circling our own planet. Those radiation belts are not an abstract hazard. An unprotected human being exposed to Jupiter's inner radiation environment would absorb a lethal dose within minutes, not days, not hours. Minutes. It is one of the most punishing radiation environments anywhere in the solar system that we have actually sent hardware into on purpose, which tells you something about how badly we wanted to look closer anyway. That is why NASA's Juno spacecraft, which launched in 2011 and arrived at Jupiter in 2016, carries its most sensitive electronics inside something engineers actually call a radiation vault. A box built from titanium, roughly a centimeter thick, shielding the computer and instruments at its core the way a bunker shields the people inside it. Without that vault, Jupiter's radiation would fry Juno's brain in a single close pass. Even with the vault, Juno is not immune, only delayed. Each close pass over Jupiter degrades its electronics a little further, radiation slowly cooking components that were never meant to last forever out there. Mission planners built the spacecraft's orbit specifically to limit the damage, tracing long, elongated loops that dive in close for a matter of hours and then swing back out to safer distance before diving in again. Jupiter's magnetic bubble, its full magnetosphere, is so enormous that if human eyes could somehow see it directly from Earth, it would appear larger in our sky than the full moon, despite sitting hundreds of millions of kilometers away. On the side facing away from the Sun, the magnetic field stretches out past the orbit of Saturn. Jupiter is not simply a large planet. It projects influence across a volume of space that dwarfs the planet itself by a staggering margin. That radiation environment does not stay politely contained around Jupiter either. It bathes the planet's inner moons constantly, Io most of all, adding a second layer of punishment to a moon that, as it happens, is already being tortured by gravity from an entirely different direction. We will get to exactly what that means for standing on Io. For now, just remember that nothing near Jupiter gets to rest. For a long time, Jupiter got cast as the solar system's bodyguard, a gravitational giant standing between Earth and the worst of what deep space might otherwise throw at us. Its gravity is certainly strong enough to capture or fling away comets and asteroids that wander too close, and there is real evidence it has done exactly that, again and again, for billions of years. In July of 1994, the world got to watch it happen in real time. Comet Shoemaker Levy 9, torn apart by Jupiter's gravity on a previous pass, broke into more than 20 fragments and slammed into the planet's southern hemisphere one piece after another over the course of nearly a week. The impacts left dark bruises in Jupiter's clouds larger than Earth itself, visible through backyard telescopes for months afterward. A live demonstration of what a planet built to absorb impacts actually looks like doing its job. It made for a genuinely comforting story. Jupiter, the big brother out there absorbing the hits, so the inner planets do not have to. The trouble is that the same gravity making that possible does not actually care which direction anything travels. Long-term orbital simulations show Jupiter has also redirected objects inward across the solar system's history, sending material toward Earth that might otherwise have drifted past harmlessly. Gravity does not choose sides. It is not loyalty, and it is not malice. It is just mass, doing what mass does to anything that wanders close enough, and it does not know or care whether the object it just redirected ends up drifting into the empty dark or landing on someone's planet. We are the ones who decided to call that protection when it worked in our favor. So hold both facts at once, the way you would about anyone genuinely powerful. Jupiter is almost certainly why the inner solar system is not more heavily bombarded than it already is. Jupiter has also, on occasion, been the reason something ended up on a collision course in the first place. The biggest thing in the neighborhood is not automatically the friendliest. Sometimes it is just the one with the most leverage, and leverage cuts however it happens to fall. On Jupiter's moon Io, the ground itself gets kneaded like dough, flexed by gravity strong enough to bend solid rock, and it never once lets up. There is no season here, no calm stretch between events. The deformation is constant, measured not in rare violent moments, but in a steady, grinding pressure that has apparently been running for as long as this moon has existed. Io was one of the 4 moons Galileo spotted circling Jupiter back in January of 1610, the innermost, and, it turns out, by far the most violent of the group. From a distance through any modern telescope, it looks almost cheerful, mottled yellow and orange like a poorly made pizza. Get closer, and that cheerful coloring turns out to be the visible residue of a moon being actively, continuously deformed by forces entirely outside its control. Io takes its name from a figure in Greek mythology, a mortal woman loved by Zeus and transformed into a heifer to hide her from his jealous wife, then driven half mad and chased relentlessly across the earth by a stinging gadfly that never let her rest. Whoever chose that name in the 1600s could not have known how well it would eventually fit. A moon name for someone tormented without pause, discovered centuries before anyone understood exactly how tormented it actually was. The mechanism behind it is called tidal heating, and it starts with a straightforward fact. Jupiter's gravity is enormous, and Io orbits closer to it than any other major moon. That alone would just mean a fast, tight orbit. What turns into torture is the company Io keeps. Io, Europa, and Ganymede are locked into what astronomers call the Laplace resonance, a precise rhythm where Io completes exactly 2 orbits for every one of Europa's, and Europa completes exactly 2 for every one of Ganymede's. That clean mathematical relationship never lets Io settle into a calm, circular path around Jupiter. Every time it starts to relax into one shape, Europa's gravity tugs it back into an elongated one instead. Picture bending a paperclip back and forth, not once, but continuously, forever, never letting it come to rest. The metal at the bend gets warm, then hot, purely from the friction of being flexed. Io is that paperclip, except the thing doing the bending is the combined gravity of a planet 300 times more massive than Earth and 2 neighboring moons, and the bending has never once paused long enough for anything to cool. The result, deep under Io's crust, is likely a layer of partially molten rock kept in a permanent state of near liquid stress. That heat has to go somewhere, and it goes up through hundreds of vents scattered across the surface, making Io the most volcanically active body anywhere in the solar system. More active than Earth, more active than every other rocky world combined. Nobody on Earth had ever seen an active volcanic eruption anywhere beyond our own planet until March of 1979, when a NASA engineer named Linda Morbido was reviewing navigation images from the Voyager 1 spacecraft and noticed a strange bright arc rising off the edge of Io. It was not a photography error. It was a plume caught mid-eruption, rising roughly 300 kilometers above the surface in a single frame that changed what we thought Io was. Since then, spacecraft have caught plumes on Io reaching considerably higher, some estimates placing material as high as 500 kilometers above the surface, roughly the altitude where the International Space Station orbits Earth. These are not gentle seeps of lava. They are eruptions with enough force to throw sulfur and sulfur dioxide clear off the moon's gravity well entirely, some of it escaping into orbit around Jupiter itself. One feature, a lava lake called Loki Patera, spans roughly 200 kilometers across, making it the most powerful volcanic hotspot anywhere in the solar system, radiating more heat on its own than every volcano on Earth put together during its active phases. It brightens and dims on a cycle that astronomers on Earth can track through telescopes, watching an alien lava lake breathe from hundreds of millions of kilometers away. The colors across Io's surface all come from sulfur in its various chemical forms, painted across the landscape in yellows, oranges, reds, and streaks of black where fresh lava has recently cooled. Features get named for fire and volcano deities pulled from mythologies around the world. Pele, Prometheus, Loki. It reads almost like the moon was cataloged by people who ran out of gentler names and simply gave up trying to find any. What makes Io genuinely unlike anywhere else we have observed is how fast it rebuilds itself. Impact craters accumulate on most solid worlds over billions of years and just sit there, slowly weathering. On Io, fresh lava buries old terrain fast enough that the surface visibly changes within a matter of years, sometimes within months, and virtually no impact craters survive long enough to be seen at all. Io is not an ancient, cratered world. It is a permanently unfinished one. On top of all that internal torment, Io sits inside Jupiter's radiation belts, the same lethal environment that forces spacecraft like Juno to hide their electronics behind titanium. Io gets no such protection. It is bombarded from outside by charged particles at the same time. Its interior is being wrung out by gravity, squeezed and irradiated simultaneously, with no direction for which relief might arrive. Io's suffering does not even stay contained to Io. Volcanic material escaping into space gets stripped by Jupiter's magnetic field and stretched into a vast donut-shaped ring of charged sulfur and oxygen circling the planet along Io's orbit, called the Io plasma torus. A moon being wrung out by gravity is, in effect, bleeding into the space around it, and that bleeding helps power the very radiation belts making the whole neighborhood so dangerous in the first place. Io does have an atmosphere. Technically, though calling it that is generous. It is a thin haze of sulfur dioxide, thick enough to matter only barely, and it does something strange twice during every orbit. When Io passes into Jupiter's shadow and loses direct sunlight, that atmosphere largely freezes onto the surface as frost, then thaws and rises again once sunlight returns. An entire moon's atmosphere, collapsing and rebuilding itself on a schedule measured in hours. Surface temperatures average somewhere around minus 143 degrees, cold enough to freeze that thin atmosphere solid. And yet active eruption sites nearby can reach temperatures over 1,300 degrees Celsius, hot enough to melt basalt. Nowhere else in the solar system sits that close to boiling and freezing within the same short walk, an entire moon permanently split between extremes with no gentle middle ground anywhere on it. Measured per square meter, Io radiates more internal heat into space than Earth does, despite being a fraction of the size and having no equivalent of Earth's radioactive core slowly decaying over billions of years to explain it. Nearly all of that heat comes from friction, from being squeezed and released by neighbors it never gets a break from. It is, in the most literal sense, a moon running a fever it did not choose and cannot break. NASA's Galileo spacecraft spent the years between 1995 and 2003 orbiting the Jupiter system and returned again and again to photograph Io, building a record of eruptions starting, spreading, and burying older terrain across repeated passes. Watching those images in sequence feels less like studying geology and more like watching a wound get reopened on a loop, the same locations flaring bright, going dark, and flaring again. Try to imagine actually standing there, if such a thing were survivable, which it is not. The ground beneath your feet would not simply support your weight the way solid rock does on Earth. Io's surface rises and falls by measurable amounts as tidal forces flex the crust in real time. A slow, continuous heave you would likely be able to detect without any instruments at all, assuming you lived long enough between one flex and the next to notice. It helps to stop thinking of Io as a planet that happens to have volcanoes on it, the way Earth does. Earth's volcanism is largely a release valve, plate tectonics slowly relieving pressure that built up over long stretches of relative calm. Io has no calm stretches. It is not erupting because pressure occasionally needs somewhere to go. It is erupting because something outside it, Jupiter, Europa, Ganymede, never stops applying the force that causes the pressure in the first place. Some planetary scientists describe Io as the closest living example we have of what a young rocky world looks like in its most violent early stretch, similar in spirit to conditions Earth itself likely endured during its molten formative period, roughly 4 billion years ago. The uncomfortable difference is that Earth eventually cooled and calmed as it aged. Nothing in Io's situation points toward it ever being allowed to do the same. It helps to look at what Io's neighbors avoided. Callisto, the fourth and outermost of the Galilean moons, sits just far enough from Jupiter to have escaped the Laplace resonance entirely. Its surface is ancient, some of the most heavily cratered terrain anywhere in the solar system, essentially unchanged for billions of years. Callisto got to have a quiet, uneventful history. Io, closer in by a matter of a few 100,000 kilometers, got none of that mercy. No spacecraft has ever attempted to land on Io, and none is seriously planned to. The radiation alone would kill electronics within a short window, on top of a surface that is quite literally unstable to build anything permanent on. Every mission that has studied it, Voyager, Galileo, New Horizons, Juno on selected passes, has done so from a distance, taking pictures and leaving fast. Io is a place we observe. It is not, for now, a place we visit. This has likely been the arrangement for as long as that orbital resonance has existed, which could mean billions of years of essentially uninterrupted deformation. There is no reason within the current physics of the system to expect it to stop. As long as Io, Europa, and Ganymede keep circling Jupiter in that same locked rhythm, Io keeps getting squeezed. There is no scheduled reprieve. There is no reprieve of any kind. So set aside the postcard version of Io, the bright mottled moon in the wide-angle photographs. What you're actually looking at is a body with no agency over its own geology, wrung out on a fixed schedule by neighbors it cannot escape and a planet it cannot outrun. Its violence not an event, but a permanent condition. Io is not a landscape. It is closer to a wound that never gets the chance to close. Under roughly 12 miles of ice on a moon of Jupiter called Europa sits more liquid water than every ocean on Earth combined, and not one human being has ever laid eyes on so much as a drop of it. We know it is there from measurements for magnetic fields and orbital wobbles and cracked ice photograph from orbit. Nobody has looked inside. Nobody currently can. Europa is the second of the 4 large moons Galileo found circling Jupiter, smaller than our own moon, wrapped in a shell of water ice so bright and smooth from a distance that early images made it look almost like a cracked egg photograph from space. That crack pattern is not decoration. It is the surface telling you, quietly, that something underneath it is moving. Europa takes its name from a different Greek myth than its tortured neighbor, a Phoenician princess who caught the attention of Zeus, who approached her disguised as a gentle white bull and carried her off across the sea toward Crete. It is a strange thing, naming 2 moons locked in the same gravitational trap after 2 separate figures pursued by the same god. Whoever chose these names in the early 1600s was only working for mythology. The universe apparently decided to make the pattern fit anyway. The same tidal forces wringing Io apart reach Europa too, just at a lower dose, since Europa orbits farther from Jupiter, where that squeezing turns Io's interior into an open wound of active volcanism. On Europa, it produces something gentler, but arguably more interesting. Just enough heat, generated deep inside, to keep a global layer of water from ever fully freezing solid despite sitting this far from the sun. There's something almost unfair about that arrangement. The exact same gravitational torment that turns one moon into a landscape of constant eruption turns its neighbor into what might be the most promising place to look for life beyond Earth in our entire solar system. Violence and possibility produced by the identical mechanism delivered to 2 different addresses. Europa's surface is covered in long reddish-brown streaks called lineae, cracks running for hundreds of kilometers across the ice, many of them doubled or braided like scar tissue. Their color likely comes from salts or sulfur compounds pushed up from below and altered by radiation at the surface. Whatever is down there does not stay perfectly hidden. Some of it keeps leaking up through the cracks and staining the ice. What genuinely surprised scientists studying Europa is how young its surface looks. Impact craters accumulate steadily on most solid bodies over billions of years, but Europa's surface shows remarkably few of them, leading to estimates that the visible ice is only somewhere between 40 and 90 million years old. That is not ancient by planetary standards. It is practically freshly poured, which means whatever process resurfaces Europa is still active right now today. In places, the ice breaks into what scientists call chaos terrain, blocks of surface that look like they have been shattered, rotated, and refrozen in slightly wrong positions. The way ice on a lake looks after it cracks and drifts before the cold catches up with it again. The leading explanation is that liquid water, or at least slush, sat close enough to the surface in those spots to let the ice above it break loose and rearrange. Set the cracks and the chaos terrain aside for a moment, and Europa is, on the whole, startlingly smooth for a body this size, with almost nothing that counts as a real mountain and nothing carved out by anything resembling erosion. Scientists sometimes compare its shape to a cue ball. The likely reason is almost poetic on its own. An ice shell resting on top of liquid water simply cannot hold up tall structures for long. Gravity and a soft foundation underneath keep sanding everything back down. The strongest evidence for an actual global ocean came from NASA's Galileo spacecraft, which studied the Jupiter system through the 1990s and measured how Europa's magnetic environment responded as it moved through Jupiter's own magnetic field. The pattern it found only makes sense if there is a layer of electrically conductive fluid under the ice, something salty, something liquid, something large enough to react to a planet-sized magnet from a distance. Estimates for that ocean's depth run from roughly 60 to 100 kilometers in places, sealed entirely under the ice, entirely without sunlight, entirely without a sky of any kind. Total it up, and there is more liquid water down there than in every ocean, sea, river, and lake on Earth combined, held inside a moon smaller than our own, in permanent darkness, at pressures and temperatures no human has ever personally experienced. What makes that ocean genuinely interesting, rather than just large, is what might be happening at its floor. If Europa's rocky interior experiences its own version of tidal flexing, and there is reason to think it does, then its seafloor could host hydrothermal vents, similar in principle to the ones discovered on Earth's own ocean floor in the 1970s. Chemical energy pouring out of the rock into the water above it. That detail matters more than it might sound like it should, because it means life would not necessarily need sunlight to get started down there. On Earth, communities of organisms live around hydrothermal vents in total darkness, deep enough that sunlight has never reached them, running entirely on chemical energy instead. If the same chemistry exists on Europa's seafloor, sunlight stops being a requirement for biology, which changes the entire calculation for where else life might be waiting. There have been hints of Europa reaching outward too. The Hubble Space Telescope detected what looked like plumes of water vapor venting from the moon's southern region in 2012 and again in 2016, jets that would, if confirmed and repeated, offer a way to sample the ocean without ever drilling through the ice at all. The detections have been inconsistent, though, present in some observations and stubbornly absent in others, which keeps the whole idea technically unproven. For years, scientists debated exactly what kind of salt gives Europa's ocean its particular chemistry, with magnesium sulfate, essentially Epsom salt, standing as an early favorite guess. More recent analysis using ground-based telescopes and the James Webb Space Telescope points instead towards sodium chloride, ordinary table salt, the same compound that makes Earth's oceans taste the way they do. If that holds up, Europa's hidden sea may be chemically closer to home than anyone originally expected. Long before real evidence for this ocean existed, the science fiction writer Arthur C. Clarke wrote a warning about Europa in his novel 2010, a fictional alien message telling humanity to stay away from the moon and land anywhere else instead. It read at the time like a plot device. Decades later, with an actual ocean confirmed underneath the ice, it reads less like fiction and more like a coincidence nobody quite knows what to do with. NASA launched the Europa Clipper mission in October of 2024, sending a spacecraft roughly the size of a basketball court, solar panels included, on a multi-year journey toward Jupiter. It is not going to land. It is not going to drill. It is going to fly past Europa dozens of times, ducking in and out of Jupiter's radiation environment the same way Juno does, gathering as much data as it can survive collecting on each individual pass. Its instruments include ice-penetrating radar, designed to measure the thickness of Europa's shell and search for pockets of water closer to the surface, along with cameras, a magnetometer to refine what Galileo first detected decades earlier, and tools built to analyze the chemistry of anything venting off the surface if a plume happens to cooperate during flyby. It is worth being precise about what this mission is actually built to do, because it is easy to overstate. Europa Clipper is not a life detection mission. It carries no instrument designed to find a microbe or confirm biology of any kind. Its job is narrower and, in its own way, more honest, determine whether Europa's ocean could plausibly support life, without claiming to answer whether it actually does. That distinction, habitable versus inhabited, is the whole shape of where this search currently stands. Scientists can tell you Europa has liquid water, probably has chemical energy, and probably has been stable enough for a very long time to give any of it a chance to matter. What nobody can tell you, and what nothing currently flying can tell you, is whether anything actually took that chance. Clipper will not reach Jupiter until the mid-2030s, and even then, the answers it returns will be indirect. Ice thickness measurements, chemical readings, magnetic field data, all of it requiring years of careful analysis afterward before anyone can say anything with real confidence. This is not a mission built for quick headlines. It is built for the kind of patient, cumulative case that science actually runs on, one data point at a time. There's a strange upside to that thick ice shell, too. Jupiter's radiation, the same kind that forces Juno to hide behind titanium, would sterilize Europa's surface within a short time if anything were exposed directly to it. The ice absorbs that punishment instead, acting as a shield for whatever the ocean below might be protecting. The same barrier keeping us out may be the only reason there is anything left worth looking for underneath it. Engineers have sketched concepts for decades of a probe that could someday melt or drill straight through Europa's ice, a cryobot descending on its own heat toward the ocean below, releasing a small submarine once it broke through. None of that exists yet in any real, funded, scheduled form. It remains a sketch, a someday, waiting on Clipper's data to even tell us where the ice might be thin enough to try. So sit with the uncertainty here deliberately, because it is the honest version of this story. The ocean is real. The chemical ingredients that life elsewhere depends on may well be present. The moon has apparently been stable enough, warm enough, and wet enough for long enough that the possibility is not remotely far-fetched. And humanity, right now, today, simply has no way to look inside and check. That gap between what might be true and what we can currently confirm is not a failure of imagination. It is 12 miles of ice sitting on top of an ocean that has never had a sky, keeping its answer exactly where it has always kept it, out of reach, for now, of everyone who has ever wondered. The rings that make Saturn instantly recognizable, the ones a child draws automatically the moment you say the word planet, are not a permanent feature of this solar system. They're falling out of the sky, slowly, continuously, and on a cosmic timescale they will be gone. What looks like the most stable, iconic image in astronomy turns out to be one of the more temporary things we have ever pointed a telescope at. Galileo saw Saturn through his telescope in 1610 too, the same year he found Jupiter's moons, and he had no idea what he was looking at. His equipment was not sharp enough to resolve a clean ring. So he described the planet as having two smaller companions pressed against its sides, like handles or ears. It took decades and better optics before anyone realized those blurry lumps were actually a flat disk of material encircling the whole planet. The rings themselves are made of countless individual pieces of water, ice, and rock, ranging from grains finer than sand up to chunks the size of a house, all orbiting Saturn independently, none of them physically connected to each other. That ice is what makes the rings so bright. Freshwater ice reflects sunlight extremely well, which is part of why Saturn's rings are visible from Earth even through a modest backyard telescope. For all their size, spanning wider than the distance between Earth and the Moon, Saturn's rings are almost absurdly thin, in places no more than about 10 meters from top to bottom, thinner in proportion than a sheet of paper laid flat across a football field. Seen edge-on from Earth, they nearly vanish entirely roughly every 15 years, an entire ring system reduced to a hairline for a few weeks at a time, before tilting slowly back into view. Where all that material came from is still genuinely debated. Leading theories point to a shattered moon or a wandering comet, torn apart by Saturn's gravity after drifting too close. Its remains spreading out into the flat disk we see today, rather than ever falling further inward or escaping outward. It is a violent origin story hiding behind one of the most peaceful-looking sights in the sky. For most of the last century, astronomers assumed the rings were as old as Saturn itself, leftover material from the same era that built the planets roughly 4.5 billion years ago. Data gathered by the Cassini spacecraft changed that assumption. The rings look chemically remarkably clean, mostly pure ice with far less dust contamination than billions of years of exposure to space should have accumulated. Clean, in this context, means young. The mechanism erasing them is called ring rain. Saturn's powerful magnetic field pulls electrically charged icy particles out of the rings and channels them along magnetic field lines down into the planet's upper atmosphere, where they simply fall in and vanish, converted into water that eventually rains out of Saturn's own clouds. Cassini measured this happening directly, watching material leave the rings and arrive in the atmosphere in real time. The volume involved is substantial. Estimates put the rate of material falling out of the rings at somewhere between several hundred and several thousand kilograms every single second, enough that scientists studying the numbers arrived at a startling conclusion. At the current rate, Saturn's rings have somewhere around 100 million years left before they are gone entirely. 100 million years sounds close to forever by human standards, and it is. It also means the rings are young rather than ancient, likely having formed sometime within roughly the last 100 to 200 million years, which puts their origin somewhere around the era dinosaurs were still walking around on Earth. Some of the creatures that lived and died on this planet may well have looked up at a sky with no rings around Saturn at all, because there was nothing there yet to see. Which means, strange as it sounds, that we are living inside a relatively narrow window when Saturn happens to look the way it does in every photograph, painting, and postcard. Earlier civilizations that never developed a telescope missed the rings entirely by circumstance of timing rather than technology. Future ones far enough out will look at Saturn and simply see a plain, ringless gas giant and have no idea what they are missing. The gap named after Giovanni Cassini himself, a dark lane roughly 4,800 kilometers wide separating two of the brightest rings, was first spotted through his own telescope back in 1675, more than 3 centuries before the spacecraft carrying his name would fly directly through a far narrower version of that same kind of gap on its way toward its own destruction. History has a way of closing loops like that without asking anyone's permission. Studying all of this closely enough to notice it was the job of a spacecraft named after the same Giovanni Cassini who once puzzled over an early version of Jupiter's Great Red Spot. Cassini launched in October of 1997, took nearly 7 years just to reach Saturn, and arrived in 2004 to begin what became one of the most productive missions in the history of planetary science. Over the following 13 years, Cassini mapped Saturn's rings in extraordinary detail, discovered active geysers erupting from a small, icy moon called Enceladus, found lakes and rivers of liquid methane on the hazy moon Titan, and tracked storms churning through Saturn's own atmosphere. It fundamentally rewrote what scientists understood about this entire part of the solar system, moon by moon, orbit by orbit. By 2017, Cassini was running low on the fuel it needed to keep adjusting its orbit and pointing its instruments correctly. The spacecraft itself was still healthy, still functioning, still capable of collecting data. The mission team faced a choice that had nothing to do with whether Cassini still worked and everything to do with what might happen to it once it stopped. Left uncontrolled, a dead Cassini would eventually drift and could plausibly, someday, crash into Enceladus or Titan, two moons considered genuinely promising candidates for hosting life, or at least the chemistry that leads toward it. Cassini had traveled from Earth, and Earth is covered in microscopic life that hitches rides on hardware, whether anyone intends it to or not. A contaminated crash could compromise those moons before anyone ever got a clean chance to study them properly. So NASA chose to destroy it on purpose instead. Rather than risk even a small, distant chance of contaminating a place that might already hold the answer to whether we are alone, mission planners designed a deliberate ending for Cassini, one that would guarantee the spacecraft could never accidentally reach either moon at all. They called it the grand finale. The plan called for 22 orbits, threading the narrow gap between Saturn's cloud tops and the innermost edge of its rings, a region no spacecraft had ever flown through before, close enough that engineers genuinely were not certain what they might encounter there. Ring particles, however small, moving at orbital speed, could have ended the mission early in a way nobody controlled. It worked, all 22 passes, each one gathering data no spacecraft had ever collected this close to the planet. Measurements of Saturn's interior, its magnetic field, the exact composition of the rings themselves right before they finished the job of falling apart. Then, on September 15th, 2017, Cassini began its final approach, aimed directly into Saturn's atmosphere with no possibility of pulling back out. Because the distance between Saturn and Earth meant radio signals took well over an hour to arrive, Cassini was entirely on its own during the actual plunge, following commands engineers had written and uploaded in advance. There was no live piloting possible. By the time anyone on Earth would know what happened, it would already be over. Engineers programmed Cassini to keep its antenna pointed toward Earth for as long as physically possible during the descent, transmitting real-time readings of Saturn's atmosphere as the spacecraft pushed deeper and deeper into air it was never built to survive. It kept sending data about the very thing that was destroying it, describing its own ending as it happened, for as long as its instruments and structure held together. The signal held for a few minutes longer than some engineers expected, a thin stream of numbers crossing more than 1 billion kilometers of empty space. And then it simply stopped. No dramatic final message. No countdown to zero. Just a steady stream of data that cut off mid-transmission as the spacecraft lost structural integrity and came apart in Saturn's upper atmosphere, absorbed completely into the planet it had spent 13 years studying. At mission control at NASA's Jet Propulsion Laboratory, engineers who had worked on Cassini for decades, some of them for their entire careers, watched that signal flatten out on their screens in real time. People who build spacecraft for a living are not typically known for crying at work. Several of them did anyway. It is a strange kind of grief, mourning a machine, but a 13-year mission tends to stop feeling like hardware somewhere along the way. What makes the ending land harder than an ordinary equipment failure is that this one was chosen. Cassini did not run out of luck or break down early. It was deliberately flown into its own destruction, on purpose, years in advance, to protect 2 moons from a threat that was never certain to happen and a form of life that has never actually been confirmed to exist there at all. That is worth sitting with for a moment. An entire engineering team spent years designing a controlled suicide for a healthy, functioning spacecraft, purely on the possibility, not the proof, that something worth protecting might be waiting on Enceladus or Titan. Nobody has been down there to check. Nobody, at the time of Cassini's death, had any confirmation at all. The caution came first. The evidence, if it ever arrives, will have to come later. There is a pattern running through everything covered in this stretch of the tour, if you have been paying attention. A belt of debris patient enough to wait millions of years between strikes. A planet whose gravity cannot tell the difference between shielding us and endangering us. A moon being wrung out with no possibility of rest. Another moon hiding an ocean nobody can currently reach. And now rings, and the spacecraft that studied them, both running out the clock in their own separate ways. So let the image of Saturn sit differently than it did before any of this. The rings are beautiful, and they're already dying quietly, right now, at a rate nobody can pause or reverse. The spacecraft that told us so died on purpose to protect a question that still, today, has no answer. Grief and wonder, it turns out, are not opposites out here. Most of the time, they are just describing the same object from two different angles. Point a spacecraft at a moon smaller than England, and normally you expect nothing. Ice, some craters, silence. Then in 2005, Cassini flew past a little moon of Saturn called Enceladus and saw something venting from its south pole. Fountains of ice and vapor, blasting hundreds of kilometers into black space. Scientists went further than photographing it. They flew the spacecraft directly through the spray, instruments open, to taste what a moon was breathing out. Enceladus itself is unremarkable to look at. A bright, cracked little snowball barely 500 kilometers across, small enough to fit inside the state of Arizona with room to spare. For decades, nobody expected much from it. It seemed too small and too cold to be doing anything at all. Then the tiger stripes appeared in the data, for long fractures near its south pole, glowing warmer than they had any right to be, pouring material into space nonstop. Cassini launched in 1997 and spent 7 years crossing the solar system before it ever reached Saturn. It was built to study rings and storms, not to go hunting for an ocean. Nobody on the mission expected a moon this small to be the discovery that mattered most. And yet within a year of arriving, Enceladus forced its way to the front of every conversation on the team. Picture the plumes themselves, hundreds of individual jets, some no wider than a fire hose, braided together into towering curtains of ice crystals climbing thousands of kilometers above the surface. Some of that spray falls back as snow. Some of it escapes the moon's gravity entirely and feeds Saturn's faint outer E-ring. An entire ring of a planet, built from one small moon quietly exhaling. Cassini's instruments broke the spray down and found water, overwhelmingly, but not pure water. Salts, silica grains that only form in hot water in contact with rock, and organic molecules, the carbon-based building blocks that on Earth every living thing is made from. None of that proves life, but it is an oddly specific shopping list for a moon that was supposed to be dead. All of it points to the same source, a liquid ocean sealed under a shell of ice tens of kilometers thick, kept from freezing solid by the endless gravitational kneading of Saturn itself. Enceladus is squeezed and flexed on every orbit, and that friction generates heat, enough heat to keep an entire ocean liquid in a place that receives almost no warmth from the sun at all. That ocean sits directly on top of a rocky core, and Cassini found evidence of something specific happening at that boundary. Hydrothermal activity, water reacting with hot rock, the same process that powers vent systems on Earth's ocean floor. On our planet, those vents are considered one of the leading candidates for where life itself may have first ignited. Enceladus appears to be running the exact same machinery in the dark. In October 2015, Cassini did something that still sounds reckless when you say it out loud. It dropped to within 49 kilometers of the moon's surface and flew straight through an active plume at nearly 30,000 kilometers an hour, instruments wide open, collecting whatever hit them. There was no second attempt if something went wrong. One pass at that speed through a spray of ice and rock. What came back was molecular hydrogen, and hydrogen is not a minor detail. On Earth, hydrogen reacting with carbon dioxide is one of the primary ways hydrothermal vent life feeds itself, a chemical process that requires no sunlight whatsoever. Finding it streaming out of Enceladus meant the moon was wet and something more. It had a working energy source sitting there in the dark, ready to be used by something if anything was there to use it. Enceladus loses something like 200 kilograms of water and ice every second through these jets, a slow, continuous exhale that has been going on for who knows how long. Over millions of years that ought to drain a small moon dry. It hasn't. Whatever engine is driving this, the tidal flexing, the heat, the plumbing beneath the ice has apparently been running long enough to still be going, and nobody has caught it slowing down yet. People on the mission team have described that result in almost embarrassed language, because scientists are not supposed to sound like this. But more than one of them has said, on the record, that Enceladus checks nearly every box you would write down if you were designing a habitable environment from scratch. Liquid water, heat, chemical energy, organic chemistry, all of it already there, already running. This is the part of the story where the tone of this whole film has to change. Up to now, every planet and moon we've looked at has been a curiosity. Strange, violent, beautiful, but distant. Enceladus is the first place where the question stops being interesting trivia and starts being a real, unresolved question with actual stakes. Is there something alive out here? Not might there theoretically be. Is there? Saturn has another moon worth being unsettled by, and it could not look more different. Titan is enormous, bigger than the planet Mercury, wrapped in an atmosphere so thick and so orange that Cassini's cameras could not even see its surface until they switched to radar and infrared. From orbit, it looks like a hazy amber marble. Nobody expected weather down there. Titan has weather anyway. Titan's atmosphere is denser than Earth's, mostly nitrogen, the same gas that dominates the air you're breathing right now, laced with methane and a thick smog of complex organic haze. It is the only moon in the solar system with a substantial atmosphere at all. Sunlight barely gets through it. Whatever direct light reaches Titan's ground arrives dim, orange, and diffuse, like a permanent late afternoon under a heavy sky. And on the ground, there is liquid. Not water, it is far too cold for that, but lakes and seas of liquid methane and ethane, the largest named Krakenmeer, big enough to be called a sea without exaggeration. Titan is the only place beyond Earth where we have confirmed stable liquid sitting openly on a solid surface. Everywhere else in this solar system, liquid stays hidden underground or doesn't exist at all. It even rains. Methane clouds build up, methane rain falls, carve channels and river networks into the terrain, pools into lakes, and slowly evaporates back into the atmosphere to start again. It is Earth's water cycle, rebuilt from entirely different chemistry, running at a surface temperature near minus 179 degrees Celsius. An alien meteorologist would recognize the shape of it instantly and be baffled by every material involved. In January 2005, the European Huygens probe detached from Cassini and fell through that orange haze for 2.5 hours, then landed, the first and still only landing ever achieved in the outer solar system. Its cameras showed rounded pebbles of water ice scattered across a damp, methane-soaked plain, sitting in what looked disturbingly like a dry riverbed on Earth. It kept transmitting for about 90 minutes before Titan itself went quiet on it. Titan is far too cold for liquid water to exist on its surface, and that alone used to be enough to write it off. But some researchers now seriously study whether an entirely different kind of biochemistry could function in liquid methane instead of water, slower, stranger, running on different rules. Nobody has found evidence of it. Nobody can yet rule it out either, and that gap is exactly the point. As if the surface weren't strange enough, Titan is also suspected to be hiding a liquid water ocean of its own, buried beneath its icy crust, kept warm the same way Enceladus is by the gravitational pull of the planet it orbits. So Titan may be running two experiments in life's possibility at once: an alien chemistry on the surface and a familiar one, water and rock, sealed away underneath it. Two moons of one planet, one small and cold, venting the raw ingredients of life directly into space where we can fly through and taste them. One enormous and hazy, running a working weather system on chemistry nobody expected to find anywhere. Neither proves anything. Both make the same quiet argument. The ingredients for something interesting are not rare here. They may simply be waiting. And these two are not isolated cases. Other icy moons across the outer solar system are now suspected of hiding oceans of their own, sealed under miles of ice, warmed by the same tidal forces. We used to think liquid water needed a sun like ours sitting close, the way Earth has it. Saturn sits nearly 1.4 billion kilometers from the sun, and its moons appear to be keeping oceans warm anyway. That changes the math on the entire search for life. It was always built on one assumption, that you need a warm, sunlit world like Earth. If moons out here in the permanent dark and cold can build and sustain oceans of their own, warm from the inside instead of from above, then the number of places worth checking in this solar system alone quietly multiplies, and we have barely started counting. We have flown through the spray of one of these oceans exactly once, for a matter of seconds, at 30,000 kilometers an hour, with instruments built years before anyone knew what to look for. That is the entire depth of our investigation into whether Enceladus holds anything alive. A few seconds, decades ago, through a fine mist at extreme velocity. It is an almost comic understatement measured against the size of the question. So carry this forward, because it changes how every remaining stop on this tour should feel. We are no longer just admiring the furniture of the solar system. We are checking, planet by planet, moon by moon, for a pulse. And the honest, uncomfortable answer, after Enceladus and Titan, is that we genuinely do not know if we are alone out here, and we are only just starting to look properly. That question, whether Enceladus or Titan hold anything alive, is not a settled debate anymore. It is an active one, with hardware already being built to chase it. NASA's Europa Clipper is already en route to another suspected ocean moon, and a rotorcraft called Dragonfly is being built to fly across Titan itself later this decade. We flew through an alien ocean once, almost by improvisation. The next missions are being built on purpose, specifically to look for what might be living in it. Enceladus is a moon most people had never heard of a generation ago, spraying its ocean into the open dark, testable, reachable, waiting on the far side of a several-year flight. That is the strange gift of this discovery. It is not abstract. It is a place. And once you have seen a moon breathing water into space, it gets very hard to look at the rest of this solar system as background scenery again. Every planet in this solar system spins more or less like a top, leaning a little, turning around a mostly upright axis. Except one. Uranus does not lean, it lies down. Its axis is tipped almost 98 degrees, so far over that the planet does not so much spin as roll along its orbit like a ball someone kicked, poles pointed nearly straight at the sun instead of straight up. To be clear about how extreme that number is, Earth's axis tilts about 23 degrees, which is already enough to give us seasons. Uranus tilts 98. Its axis has tipped past sideways entirely and started leaning back the other way. Nothing else in the solar system comes remotely close to lying this flat on its orbital path. Uranus was not always known as a planet at all. Ancient sky watchers tracked 5 bright wandering stars against a fixed background for thousands of years and never flagged this one. It is faint enough and moves slowly enough to pass for an ordinary star. William Herschel spotted it through a homemade telescope from his garden in Bath, England, in 1781, and assumed at first he had found a comet. It took months of watching it barely move before astronomers accepted this was the first planet discovered in recorded history that nobody had ever known was there. Herschel wanted to name his discovery after his patron, calling it Georgium Sidus, George's star, and British astronomers used exactly that for decades while the rest of Europe quietly refused to name a planet after a living king. It eventually settled on Uranus, the personification of the sky itself in Greek myth, father of Saturn, grandfather of Jupiter. It remains the only planet named for a Greek god rather than a Roman one, and professional astronomers have been mildly wincing at pronouncing it out loud in public ever since. Nobody thinks Uranus was built this way. The leading explanation is violet. Sometime in the planet's early history, roughly billions of years ago, while the solar system was still a shooting gallery of debris, something enormous, possibly a body close to the size of Earth, slammed into it. The collision did not destroy the planet. It just knocked it over, and it never got back up. You can still read the aftermath of that impact and the details around Uranus today. Its moons and thin rings orbit around the planet's tipped equator rather than the solar system's flat plane, meaning the whole system got dragged sideways along with the planet, not just the planet alone. Its interior heat distribution is unusually cool for a world its size. Something old and catastrophic happened here, and the planet has been carrying the evidence ever since. That tilt rewrites what a season even means. Uranus takes 84 Earth years to complete one orbit of the Sun, and because its axis points almost directly at its star for part of that orbit, one pole spends 21 consecutive years in continuous daylight, while the other sits in 21 consecutive years of unbroken night. Then, slowly, the roles reverse. A single human lifetime is not long enough to see Uranus go through even one full cycle of its own seasons. Try to imagine actually standing at one of those poles. The sun does not rise and set. It just circles low and slow around the sky, day after day, year after year, for 2 decades straight. And then it sinks and does not come back for another 21 years. 2 full generations of unbroken light, followed by 2 full generations of unbroken cold and dark. Nothing on Earth prepares you to picture a day that long. Astronomers group Uranus and its neighbor Neptune into their own separate category, ice giants, distinct from bloated gas giants like Jupiter and Saturn. The name is a little misleading. There is no ice sheet to walk on. It refers to a deep mantle of compressed water, ammonia, and methane, wrapped in a thinner outer layer of hydrogen and helium than Jupiter or Saturn carry. Underneath all of it, Uranus is built from a genuinely different recipe than its bigger siblings. From a distance, Uranus reads as a pale, featureless blue-green marble, almost eerily calm compared to Jupiter's churning storms. That color comes from methane gas high in its atmosphere, which absorbs red light and reflects the cooler end of the spectrum back at us. It looks serene. It is not. Beneath that placid surface sits some of the strangest physics of any planet we have found. That calm is not permanent either. As Uranus approached its equinox in 2007, the rare moment when sunlight falls evenly across its equator instead of baking one pole for decades, Hubble caught bright storm systems flaring across its atmosphere that had never shown up in Voyager's brief flyby data. Winds inside those storms have been clocked at several hundred kilometers per hour. The bland blue marble everyone remembers from 1986 turns out to have weather. We simply were not looking at the right moment to catch it. Despite sitting billions of kilometers closer to the Sun than Neptune, Uranus somehow holds the record for the coldest atmospheric temperature ever measured on any planet in the solar system, dropping to roughly minus 224 degrees Celsius in its upper atmosphere. Neptune, farther out and by all logic colder, actually radiates more heat outward from its interior than Uranus does. Something about that ancient collision may have left Uranus running strangely cold from the inside out, and nobody has a fully settled explanation for why. Deeper inside, pressure climbs to levels that do genuinely strange things to ordinary matter. Methane in that mantle, under enough heat and crushing pressure, may break apart, and its carbon may be squeezed into solid crystal form. Not metaphorically, actual diamonds, forming in the slush deep inside Uranus, and by some models, slowly raining downward through the mantle toward the core. This is not pure speculation. Physicists have recreated those pressures on Earth, briefly, using diamond anvils and powerful laser pulses to squeeze hydrocarbon samples for fractions of a second, and watch tiny diamonds form in the lab under exactly the conditions modeled for Uranus's interior. We cannot go look at the rain itself. We can reproduce the weather in miniature in a laboratory and trust the extrapolation. Uranus even has rings, though almost nobody pictures them when they picture the planet, because they were found entirely by accident. In 1977, astronomers watched Uranus pass in front of a distant star, planning to time how the star's light dimmed to measure the planet's atmosphere. Instead, the star blinked off and on several times before Uranus ever got there, and again after it left. Something unseen was blocking the light. Rings nobody had ever imagined. Uranus's rings are nothing like Saturn's. They are narrow, dark as charcoal, made of particles that reflect almost no light at all, which is exactly why nobody had spotted them by eye through a telescope for 2 centuries. Saturn's rings announced themselves. Uranus's rings had to be caught in the act of blocking starlight before anyone knew to look for them at all. By now, astronomers have cataloged 13 faint rings and at least 27 moons around Uranus, more moons than any planet except Jupiter and Saturn. Every single one of them, every ring and every moon, orbits tipped over on that same sideways axis, dragged into the same 98-degree lean as the planet itself. It is a whole miniature solar system, moons and rings alike, still carrying the tilt of one very bad day, roughly 4 billion years ago. The planet's moons carry their own scars. They're named for characters out of Shakespeare and Alexander Pope, rather than mythology: Titania, Oberon, Ariel, Umbriel, and they orbit tipped over right alongside their parent planet. Several show surfaces that look violently reshaped rather than gently formed, more evidence, in miniature, of a system that had something catastrophic happen to it early on and never fully settled afterward. The strangest of them is tiny Miranda, barely 470 kilometers across, covered in a chaotic patchwork of canyons, ridges, and grooves that do not connect to each other in any way that makes geological sense. One cliff face, Verona Rupes, drops an estimated 20 kilometers, among the tallest known cliffs in the solar system. Some scientists think Miranda was shattered by an impact and gravitationally reassembled itself, badly, out of its own wreckage. Every image you have ever seen of Uranus up close, every direct measurement of its rings, its moons, its magnetic field, comes from a single spacecraft, on a single pass, on a single day. Voyager 2 flew by on January 24th, 1986, came within about 81,500 kilometers of the cloud tops, and kept going. It never orbited. It never looked back. That flyby remains the only time humanity has ever visited this planet in person. Voyager 2 did find something nobody expected on the way past: a magnetic field wildly out of alignment with the planet itself, tilted about 59 degrees from Uranus's rotation axis and offset far from the planet's actual center. As Uranus spins, that lopsided field corkscrews out behind it like a badly balanced tire wobbling down a road. Nobody has fully explained why the field sits so strangely off-center, only that it does. That was 1986. There's been no orbiter since, no lander, no return mission of any kind for 4 decades and counting. Everything learned about Uranus since that single flyby has come from telescopes sitting safely on or near Earth, from Hubble's periodic snapshots to newer adaptive optics on ground-based observatories, all of it squinting at a small pale from nearly 3 billion kilometers away. Compare that to what we just spent an entire chapter doing at Saturn, flying a spacecraft directly through an ocean moon's exhaled breath. Uranus has never gotten anything close to that kind of attention. Not because it is less interesting, By nearly every measure, it is one of the strangest planets we have. It has simply never made it to the front of the line. In 2022, the leading planetary science community finally ranked a dedicated Uranus mission as its top priority large-scale project for the coming decade, a proposed orbiter and atmospheric probe. Even on an optimistic schedule, it would not launch before the early 2030s and would not arrive at Uranus until sometime in the 2040s. A planet tilted onto its side, still waiting, the way it has been waiting since 1986, and the way it was already waiting for billions of years before that. There is something quietly unsettling about that gap. Every world we have looked at so far in this film has felt, at least a little, like it was performing for us. Rings, storms, geysers, something to point a camera at. Uranus just sits out there, tipped on its side, running its impossibly long seasons in near total silence, indifferent to whether anyone is watching or not. And it will keep doing that, alone, for as long as anyone can currently plan for. Somewhere on Uranus right now, one pole is deep into a decade of unbroken night, the other locked in a decade of unbroken day, both of them simply waiting out a season that will not finish before most of us are gone. It has been rolling along that same tip path for roughly 4 billion years, and it is not going to stop rolling now. On the night of September 23, 1846, an astronomer in Berlin pointed his telescope at one specific tiny patch of sky. He was not searching, he was checking. A letter from Paris had told him almost exactly where to look, down to a fraction of a degree, for a planet nobody had ever seen. Within an hour, there it was, sitting nearly exactly where the letter said it would be. To understand how strange that is, go back further to Uranus, the planet we just spent an entire chapter with. For decades after its discovery, astronomers tracked its orbit against the predictions of Newtonian gravity, and Uranus kept refusing to cooperate. It drifted slightly ahead of schedule, then slightly behind, small deviations but real ones, and they kept accumulating instead of canceling out. The mismatch had been building for decades before anyone did anything about it. French astronomer Alexis Bouvard published orbital tables for Uranus in 1821, confidently predicting exactly where it would sit in the sky for years to come. Uranus almost immediately started drifting off those predictions, and the gap kept widening instead of correcting itself. By the 1840s, that drift amounted to roughly 2 arc minutes, far too small to notice with the naked eye, but glaringly obvious to anyone tracking it with a telescope and a logbook. By the 1840s, this had become a genuine problem, not a curiosity. Either Newton's law of gravity, the foundation of essentially all physics at the time, was subtly wrong, or something else was out there, some unseen mass, far beyond Uranus, tugging on it with its own gravity and throwing its orbit slightly out of line. Nobody wanted to bet against Newton, so astronomers went looking for the second explanation instead. That meant solving a problem that had essentially never been attempted before, working backward from the wobble in a known planet's orbit to calculate the exact mass, distance, and position of a planet that had never been observed by anyone. Not searching the sky and hoping to spot something new. Starting from pure arithmetic and demanding that the universe produce a planet at a specific coordinate on command. A French mathematician named Urbain Le Verrier took on that problem in 1845 and spent months buried in hand calculations, adjusting and refining, treating Uranus's misbehavior as a kind of encoded message about something hiding in the dark. He had never looked through a telescope to do any of this. He did not need to. He was arguing directly with the mechanics of the solar system, using nothing but pen, paper, and Newton's laws. Solving it took more than recent observations. Astronomers dug up archival sightings of Uranus recorded long before Herschel ever recognized it as a planet, including one log by the English astronomer John Flamsteed all the way back in 1690, who had written it into his star catalog as an ordinary star without realizing what he was actually looking at. Le Verrier folded a century and a half of accidental sightings into his calculation, squeezing every scrap of positional data out of records nobody had ever thought to use this way. He was not actually alone in this. In England, a young mathematician named John Couch Adams had been chasing the same calculation even earlier, quietly, without much support from the astronomers around him. His numbers were promising too, but the British observatories that could have gone looking moved slowly, distracted and skeptical, and the search never got properly underway before Leverrier's letter reached Berlin first. Leverrier finished his calculation in the late summer of 1846 and, frustrated by French astronomers who were in no hurry to check his work, wrote instead to Johann Galle at the Berlin Observatory, a total stranger, handing over precise coordinates and essentially daring him to look. Galle received the letter on September 23rd. He and a student, Heinrich d'Arrest, aimed the observatory's refractor at the sky that same night. They compared what they saw against a recent star chart of that region, checking every point of light against what was already known to be there. Almost immediately, one object did not belong. A faint blue-tinged point sitting almost exactly within about 1 degree of where Leverrier's arithmetic said a planet had to be. They had found it in under an hour of actually looking. Galle reportedly turned to young d'Arrest at the eyepiece that night and said something close to, "That star is not on the chart. We should have a closer look." They spent barely another half hour confirming it, watching for the object to shift slightly against the fixed stars behind it. That small movement was the one sure sign, in that era of astronomy, that you were looking at a planet and not simply another star. Sit with how backward, that is, compared to every other planet discovered before it. Mercury, through Saturn, had been visible to the naked eye since before recorded history. Even Uranus, for all its strangeness, was found the ordinary way, by scanning the sky and noticing something that moved. Neptune was different. Neptune was found on paper first, and only afterward confirmed to actually exist by pointing an instrument at the exact spot the numbers demanded. The credit dispute that followed was messier than the discovery itself. French astronomers wanted the moment to belong entirely to Leverrier. British astronomers, embarrassed at having sat on Adams's earlier calculations, pushed hard to have him recognized as a fellow discoverer after the fact. The argument dragged on for years, occasionally turning openly nationalist, before history settled into an uneasy compromise crediting both mathematicians alongside the man who actually pointed the telescope. Even naming the planet turned into a small tug of war. Leverrier, not shy about his own achievement, initially suggested naming it after himself. The international astronomical community was not interested in that precedent and settled instead on Neptune, Roman god of the sea, a fitting name for a world that turned out to be a deep, saturated blue the moment anyone got a proper look at it. Neptune sits almost 4.5 billion kilometers from the Sun on average, so far out that it takes roughly 165 Earth years to complete a single orbit. It has been tracked since 1846, which means it only finished its first full lap since being discovered in 2011. Everyone alive today has watched Neptune complete a smaller fraction of one orbit than the length of an average human lifetime. Like Uranus, its color comes from methane in the upper atmosphere absorbing red light and letting blue scatter back toward us. But Neptune's blue runs noticeably deeper and richer than Uranus's paler shade, and methane alone does not fully account for the difference. Something else in that atmosphere is contributing to the color, and researchers still do not have a complete answer for exactly what it is. What Neptune lacks in mystery around its color, it makes up for in violence overhead. It holds the record for the fastest sustained winds anywhere in the solar system, clocked at over 2,100 kilometers per hour, fast enough to circle the entire planet in about 16 hours. For comparison, that is well beyond the strongest hurricane wind speeds ever measured on Earth, sustained, not gusting, as an ordinary weather pattern. Voyager 2 caught direct evidence of that violence during its 1989 flyby, photographing a storm system roughly the size of Earth swirling in Neptune's southern hemisphere, nicknamed the Great Dark Spot. It looked at the time like a smaller cousin of Jupiter's centuries-old Great Red Spot. Then, when Hubble checked back in 1994, the Great Dark Spot was simply gone, and a new dark spot had appeared somewhere else entirely. Neptune has rings too, thin and dark like Uranus's, found through that same trick of watching a background star blink out as the planet drifted in front of it. Its faint arcs of ring material carry the names of the very people who spent years fighting over credit for finding the planet itself. Leverrier, Adams, Gal. A strange, backhanded kind of peace treaty written permanently into the rings of the world their argument was actually about. That churn is genuinely strange when you consider how little energy Neptune actually receives. Sunlight out, there is roughly 900 times weaker than what reaches Earth, barely enough to call daylight at all. And yet Neptune's atmosphere is somehow more violently active than Uranus's, which sits far closer to the Sun and receives noticeably more warmth. Neptune appears to be generating a substantial amount of its own internal heat and driving its winds off that instead of sunlight. Just as with Uranus, everything we know about Neptune up close comes from one spacecraft, one pass in August 1989, Voyager 2's final planetary encounter before it left the planets behind entirely and headed for interstellar space. No orbiter has ever been sent. No probe has ever descended into that howling atmosphere. Every image, every wind measurement, every detail of the Great Dark Spot came from a single flyby decades ago. There is one more coincidence worth sitting with before we leave 1846 behind. Just 17 days after Gal's discovery, a British brewer and amateur astronomer named William Lassell pointed his own telescope at the new planet and found something orbiting it, a large moon, later named Triton. Nobody thought much about its orbit at the time. It would take more than a century for astronomers to realize Triton was moving backward against the direction Neptune itself spins, which is not something an ordinary moon is supposed to do. Which brings the story back around to the method that found Neptune in the first place, because it did not stop being useful in 1846. Astronomers today find planets orbiting other stars entirely light years away using the same basic trick. Watching a star wobble almost imperceptibly and calculating backward to the unseen planet causing it. Gravity leaves fingerprints. You do not need to see something directly to know with real confidence that it is there. And that should sit a little uncomfortably, because if an entire planet bigger than Earth, sitting billions of kilometers away, could hide from every telescope on the planet until one man's arithmetic dragged it into view, the obvious next question is what else might currently be doing the exact same thing? What else is out there right now, tugging faintly at something we can already see, waiting for someone patient enough to do the math? Keep that question in your pocket, because it is going to come back before this film is over, and not as an abstraction. There really is, right now, a serious scientific argument being made about another unseen mass out past everything we have looked at so far, inferred exactly the way Neptune was from the way it quietly tugs at objects we can actually see. We are not finished with equations, finding planets before eyes do. For now, picture Neptune simply as it is, the loneliest of the 8 official planets, wrapped in winds faster than anything else in this solar system produces, so far from the sun that sunlight takes over 4 hours just to reach it, a world that mathematics found before human eyes ever confirmed it was real. It was there in the dark the entire time. We just had to do the arithmetic to notice. Watch Neptune's largest moon long enough, and something about it stops making sense. Triton crosses Neptune's sky in the wrong direction, orbiting backward against the same spin the planet itself is turning through. Every other major moon in the solar system, ours included, moves the same way its planet rotates, a family resemblance left over from how they were born. Triton breaks that pattern completely, and that single fact is the signature of a moon that was never born here at all. That backward motion is not a minor quirk. It rules out an entire category of origin story. Moons that form alongside their planet, out of the same spinning disk of leftover material. inherit that disk's rotation and orbit forward, the same direction the planet spins. Triton's orbit runs directly against it. Whatever built this moon, it did not happen in orbit around Neptune. The leading explanation is that Triton was never Neptune's to begin with. It almost certainly formed far out in the Kuiper Belt, the same distant belt of icy leftovers we'll spend our next stop exploring as an independent world roughly the size of Pluto on its own orbit around the Sun. At some point, billions of years ago, it wandered close enough to Neptune to get caught. Simply passing close to a planet is not usually enough to get captured. Gravity tends to just bend your path and send you onward. The theory that best fits Triton involves a binary, two icy bodies locked in orbit around each other, the way roughly half of all known Kuiper Belt objects seem to be. When that pair wandered too near Neptune, the planet's gravity likely flung one companion away entirely and yanked the other into a permanent, backward orbit. Triton was the one that got kept. Whatever moons Neptune may have already had before that encounter almost certainly did not survive it. A large, oddly orbiting captive dragged into the neighborhood would have thrown every existing moon's path into chaos, flinging some into collisions and ejecting others outright. Neptune's tidy, modern moon system looks less like something formed gently over time and more like the rebuilt wreckage left behind after Triton crashed the party billions of years ago. Triton itself is substantial, roughly 2,700 kilometers across, larger than Pluto and easily the seventh biggest moon in the entire solar system. And unlike most captured objects, which tend to settle into cold, dead, cratered lumps, Triton turned out to be one of the small handful of moons anywhere in the solar system that is still geologically active today, billions of years after whatever violence brought it here. Triton and Pluto are close enough in size and makeup that some scientists effectively treat them as sibling worlds, born in the same distant nursery out of similar ice and rock. The difference is entirely about what happened next. Pluto stayed out in the Kuiper Belt, quietly orbiting the Sun on its own terms. Triton wandered too close to a giant and got claimed. Same raw materials, wildly different fates, depending entirely on whose gravity happened to be nearby. Its surface looks like nothing else Voyager 2 photographed on its entire grand tour. Pale pink and white frost, nitrogen and methane ice, spreads across terrain, nicknamed Cantaloupe Terrain for its strange, dimpled, wrinkled texture, unlike any crater field or lava plain found elsewhere. Almost no impact craters mark it at all, a strong sign that whatever is happening on Triton's surface keeps resurfacing it, erasing its own history as it goes. It is also brutally cold, among the coldest surfaces ever directly measured anywhere in the solar system, sitting around minus 235 degrees Celsius. At that temperature, nitrogen itself freezes solid, which is exactly what coats much of Triton's surface, a thin, semi-transparent crust of frozen nitrogen ice lying directly on the ground like packed snow that never once has melted. Voyager 2 swept past Triton in August 1989, its final close encounter with any moon before leaving the planets behind for good. Its cameras caught something nobody expected from a world this cold and this far from the Sun. Active eruptions caught directly in the act, firing dark material upward into a barely their atmosphere. Those geysers throw plumes of nitrogen gas and dark dust up to about 8 kilometers above the surface, where high-altitude winds catch the material and drag it sideways into long, dark streaks stretching well over 100 kilometers downwind across the pale ice. Voyager caught several of them mid-eruption, black smudges frozen in a single photograph, evidence of a moon that should, by every intuitive measure, be completely inert. Triton does have an atmosphere, though barely enough to deserve the word. A thin haze of nitrogen with surface pressure roughly 70,000 times weaker than Earth's. It is thick enough to support faint clouds and hazes, and just thick enough to catch the material blasted out of those geysers and drag it sideways into the long dark streaks Voyager photographed. Thin as it is, that atmosphere is doing real, active work on the surface below it. That single Voyager 2 pass in 1989 remains the only visit Triton has ever received, the same as Uranus, the same as Neptune itself. No follow-up mission has ever launched. Proposals for a dedicated Triton orbiter have circulated among scientists for years, drawing genuine enthusiasm, and have so far lost out every time to other targets. Everything we know about this moon's geysers, its terrain, its atmosphere, comes from a handful of photographs taken during a few hours 35 years ago. The likely mechanism is almost embarrassingly simple once you hear it. Weak sunlight, filtered through Triton's translucent layer of frozen nitrogen, still carries enough warmth to slightly heat the ice from underneath, trapped there the way a greenhouse traps heat under glass. Pressure builds beneath the surface until it finds a weak point and blows, launching nitrogen gas and dark dust skyward. No internal heat required. Just sunlight this far out, still doing something, however faint. There's a real possibility Triton is hiding something else beneath that frozen nitrogen crust, a liquid water ocean of its own, kept from freezing by heat generated deep in its history and possibly still lingering today. If true, Triton would join Enceladus and Titan on the growing list of outer solar system moons, quietly keeping water liquid in places that should be nothing but frozen rock. The list of worlds worth checking keeps growing every time we look closely at one. That heat likely traces back to Triton's arrival itself. When Neptune first captured it, Triton's orbit would have been a wild, stretched-out ellipse, nothing like the nearly perfect circle it traces today. Tidal forces spent millions of years grinding that eccentric orbit down into a circular one, and all the friction involved in that process generated enormous heat, quite possibly enough to melt an ocean into existence in the first place. The same tidal machinery that once built Triton's ocean is the machinery that is now, slowly, unbuilding the moon itself. Here is where Triton's backward orbit stops being a mere oddity and starts being a countdown. Ordinary moons that orbit the same direction their planet spins, our own moon included, get gently nudged outward over time by the tidal bulge they raise on their planet, drifting slowly farther away with every passing millennium. Triton's orbit runs the opposite direction, and that reversal flips the whole exchange on its head. Because Triton moves against Neptune's spin, the same tidal forces that push a normal moon outward instead drag Triton inward, bleeding a small amount of orbital energy away on every single pass. It is an almost imperceptible loss, a matter of centimeters most years. But it does not reverse, and it does not stop. Every orbit brings Triton very slightly closer to the planet than the one before it. Current models put the ending at roughly 3.6 billion years from now, when Triton will have spiraled close enough for Neptune's gravity to overpower the moon's own structural cohesion, a boundary astronomers call the Roche limit. Cross that line, and a moon does not survive intact. Triton is, right now, on a slow, silent, mathematically certain approach toward its own dismantling. What happens after that split is one of two things. Most models suggest Triton will be shredded into a debris field circling Neptune, potentially building a ring system that could rival or even exceed Saturn's, at least for a while. A smaller share of that wreckage, or possibly the moon's surviving core, may instead plunge directly into Neptune's atmosphere. Either way, the moon we are looking at right now does not exist in 3.6 billion years. Sit with that timescale for a second, because it is almost impossible to hold in your head honestly. Complex life has existed on Earth for something like 600 million years. Triton's remaining lifespan as a moon is roughly 6 times longer than that entire span. No civilization we can currently picture, no species, arguably no version of curiosity itself, as we understand it, will exist to watch the ending. And yet the ending is not in doubt. It has already been decided by physics. It is worth thinking back for a moment to Saturn's rings and the possibility that they're not ancient decoration either, but debris from some earlier moon that met a fate very much like the one waiting for Triton. Ring systems across this solar system may not be primordial jewelry at all. They may simply be graveyards, the visible aftermath of moons that already finished the exact countdown Triton is running right now. There is something particularly bleak about how passive this all is. A few chapters back, a spacecraft made a choice, a deliberate, engineered dive into Saturn, an ending someone decided on. Triton's ending was never chosen by anyone. It was set the moment gravity first bent a wandering Kuiper belt object into the wrong orbit around the wrong planet, billions of years before anything on Earth had eyes to watch it happen. None of this makes Triton unique, only more advanced along a path every moon is quietly walking. Our own moon is doing the opposite right now, drifting a few centimeters farther from Earth every year, so slowly that it will take billions of years to matter. Every moon in every system is locked into some version of this exchange, gaining ground or losing it, and almost none of it moves fast enough for any of us to ever notice happening. So picture Triton as it actually is today, still frosted pink and white, still venting nitrogen geysers into a sky nobody is watching, tracing its backward path around a planet it was never born to orbit. Nothing about it looks urgent. Nothing about it looks like it is ending. And underneath that stillness, the arithmetic is already running patiently toward a date that was fixed the moment Neptune caught it. Stand on Pluto's surface at what passes for noon there and look up. The sun is still the brightest thing in that sky, brighter than anything else, but at nearly 5.9 billion kilometers away, it has shrunk down to something closer to a single, exceptionally brilliant star than the wide, warm disk we know here. That thin, cold, star-like daylight is genuinely what noon looks like at the edge of the solar system we have actually mapped. Pluto was found the hard way in 1930 by a 24-year-old Kansas farm boy named Clyde Tombaugh, comparing photographic plates of the same patch of sky night after night, hunting for a single point of light that had moved. He was chasing a predicted ninth planet based on calculations that later turned out to be essentially wrong. He found Pluto anyway, through sheer, stubborn visual diligence, not because the math that sent him looking was actually correct. An 11-year-old English girl named Venetia Burney suggested the name over breakfast with her grandfather, who passed it along to the observatory. Pluto, Roman god of the underworld, ruler of a cold, distant, hidden realm, felt exactly right for a world that sat that far from the sun. She was paid as thanks 5 pounds. For most of the 20th century, that name was nearly all anyone had. Even the best telescopes on or near Earth could only resolve Pluto as a soft, blurry smear a handful of pixels wide. Astronomers argued for decades over its size, its color, even basic facts about its surface, working almost entirely from guesswork and indirect measurement. As late as the 1990s, humanity's mental image of Pluto was still closer to an artist's impression than an actual photograph. NASA's New Horizons launched in January 2006, the fastest spacecraft ever sent from Earth, and still needed 9.5 years just to cross the distance to Pluto. It could not slow down and enter orbit either. It was moving too fast for that to be an option. This would be one single, high-speed pass, everything New Horizons would ever learn about Pluto captured in a matter of hours before it kept flying onward into the dark. That flyby happened on July 14, 2015. After 9.5 years of travel, the spacecraft's closest approach lasted only minutes, and the mission team would not even get confirmation the encounter succeeded until hours later, once New Horizons phoned home again from the far side of Pluto. It was, by a wide margin, humanity's most patient photograph ever taken. What came back overturned decades of assumptions in a single afternoon of data. Pluto's most famous feature, a vast, pale, heart-shaped region now named Tombaugh Regio after its discoverer, dominates one hemisphere. Its western lobe, called Sputnik Planitia, is an enormous glacier of frozen nitrogen ice roughly the size of Texas, and it is not sitting still. It is slowly, visibly churning, like a pot of something thick barely simmering. Along the edges of that nitrogen glacier stand mountains built from something else entirely: water ice, rising as high as roughly 3,500 meters. At Pluto's temperatures, water ice is not soft or slushy. It behaves like solid bedrock, hard enough to hold up entire mountain ranges. Those peaks appear to float, iceberg-like, in the slower flowing nitrogen ice around them, an alien coastline built from two different kinds of ice acting like two entirely different materials. None of that should be possible on a world this small, this cold, this far from any meaningful source of warmth. Small icy bodies are supposed to go geologically dead relatively quickly, radiating away whatever heat they started with and freezing into inert, unchanging lumps within a few 100 million years. Pluto shows signs of the opposite: active resurfacing, possible ice volcanoes, a surface that looks disturbingly young in places where it should look ancient. The leading explanation for that activity circles back to something we have heard before on this tour. Data from New Horizons is consistent with a liquid water ocean hiding beneath Pluto's icy shell, kept from freezing solid by heat from radioactive decay deep in its rocky core, and possibly by antifreeze compounds mixed into the water itself. Add Pluto to the growing list of worlds in this solar system, quietly keeping an ocean where nobody expected one to survive. Sit with how complete that reversal is. For most of a century, Pluto was the punchline of the solar system, a presumed dead ball of rock and ice too small and too far away to be doing anything interesting at all. One afternoon of close-range data turned it into an active, complicated, startlingly alive-looking world with mountains, glaciers, and a plausible ocean, all photographed for the first time by a spacecraft that only got one chance to look. Here is the strange timing of all. Just months before New Horizons even launched, in August 2006, the International Astronomical Union voted to strip Pluto of its planet status entirely, reclassifying it as a dwarf planet. The spacecraft that would eventually reveal Pluto to be more geologically alive than almost anyone expected was already built and headed there while astronomers back on Earth were formally deciding it did not count as a full planet anymore. That vote was not really about Pluto at all, not at first. In 2005, astronomers spotted Eris, a Kuiper Belt object initially thought to be even larger than Pluto. Suddenly, the astronomical community faced a real choice. Either start admitting a growing list of similar icy bodies as new planets one after another, or finally sit down and define, with actual rigor, what the word planet is even supposed to mean. The definition the IU settled on has three parts. A planet must orbit the sun, must be massive enough for its own gravity to pull it into a roughly round shape, and must have cleared its orbital neighborhood of other debris. Pluto passes the first two easily. It fails the third, sharing its orbital region with a swarm of other Kuiper Belt objects it has nowhere near enough gravity to sweep aside. It is worth reframing that whole controversy, because demotion is really the wrong word for what happened. Nobody had ever rigorously defined what a planet is before that vote, going back to antiquity, when the word simply meant wandering light in the sky. The Pluto fight forced astronomy to finally do that work properly for the first time in the history of the field, rather than continuing to rely on a definition nobody had ever actually written down. The public did not experience it that way at all. Pluto had been a planet, full stop, in textbooks and classrooms for 76 years, and plenty of people were furious to see it stripped of the title by a vote most of them had never heard was happening. Bumper stickers appeared defending it. Some professional astronomers still openly argue the IU's definition is flawed. Pluto remains, to this day, one of the very few scientific reclassifications people get genuinely angry about. Whatever you call it, Pluto is only one resident of a much larger neighborhood. The Kuiper Belt is a vast ring of icy bodies starting roughly around Neptune's orbit and stretching far beyond it, home to hundreds of thousands of objects large enough to matter, leftover debris from the same disk of material that built every planet in this film so far. Pluto is simply the largest one we happen to find first. That makes the Kuiper Belt something closer to a time capsule than a junkyard. Most of that material has sat out there largely undisturbed since the solar system itself was assembling roughly 4.6 billion years ago, too cold and too far from anything to be reshaped the way material closer to the sun has been reshaped again and again. Studying it is, in a real sense, studying frozen fossils of the solar system's own birth. Push out past the Kuiper Belt's main crowd, though, and the orbits start getting genuinely strange. A small number of objects out there follow paths so long and so stretched out that they barely fit any standard model of how the solar system formed. The most famous is Sedna, discovered in 2003, a small, reddish world on one of the most extreme orbits ever recorded for anything bound to our sun. Sedna's orbit takes an estimated 11,400 years to complete a single lap, swinging from about 76 astronomical units at its closest approach to the sun out to nearly 900 astronomical units at its farthest, roughly 20 times farther out than Neptune ever gets. For almost the entirety of that orbit, Sedna sits in a stretch of space so remote and so dim that sunlight barely qualifies as light there at all. Nothing in our current understanding of how the solar system formed cleanly explains an orbit shaped like that. Something had to stretch it out that far, some gravitational influence acting on Sedna long ago, or acting on it still, and whatever that influence was, it left this same fingerprint, faint but readable, in the shape of the orbit itself. Sedna is not alone in that oddity either. Since its discovery, astronomers have found a handful of other extreme trans-Neptunian objects, and a striking number of them share a suspicious pattern. Their orbits cluster together, tilted and oriented in roughly the same direction, as if something out there has been quietly herding them into alignment. That kind of clustering is exactly the sort of thing that does not happen by accident. In 2016, astronomers Konstantin Batygin and Mike Brown proposed an explanation that should sound familiar by now. An undiscovered planet, likely somewhere between 5 and 10 times the mass of Earth, orbiting hundreds of astronomical units out into the dark, its gravity slowly herding these distant objects into their strangely aligned, stretched-out paths. They call it Planet 9. It would be found using precisely the same detective method that found Neptune in 1846, reading a gravitational fingerprint left behind in the orbits of things we can actually see. Years of dedicated searching with some of the largest telescopes on Earth have not turned up a confirmed direct sighting of it. If Planet 9 is out there, it is far enough away and dim enough that finding it directly may take purpose-built surveys years more to accomplish. For now, exactly like Neptune once was, it exists only as an inference, a shape drawn in the way other objects are quietly being pulled around by something we cannot yet see. So the edge of the solar system, the part of it we like to think of as mapped and finished, is not actually finished at all. It is a dim, mostly silent frontier where the full inventory of what is actually out there remains genuinely incomplete, and where the honest, uncomfortable possibility remains open that something planet-sized has been sitting out there the entire time, patient, unlit, uncounted. Picture that thin, star-like sunlight on Pluto one more time, and then keep pushing outward past it, past Sedna's farthest point, into a darkness our best telescopes still cannot promise they have fully searched. That is the actual edge of what we know, not a wall, a twilight zone, dim and enormous that we're still, slowly, trying to finish counting. October 19th, 2017. A telescope perched on a dormant volcano in Hawaii, called Pan-STARRS, catches a faint smear of light moving in a way nothing native to this solar system moves. It is fast. It is strange. Within days, the astronomers tracking it realize it is not orbiting the sun at all. It is just passing through. By the time anyone points a serious telescope at it, the object is already leaving, and there are only weeks left to look before it disappears for good. They name it Oumuamua, a Hawaiian word that roughly translates to scout or messenger reaching from the distant past. It feels right. This is not a rock kicked loose from the asteroid belt. Its path bends through the solar system on a hyperbola, the kind of trajectory that only makes sense if the sun's gravity never actually held it. It came from somewhere else, it is going somewhere else, and Earth simply happened to sit in between. The astronomer who first flagged it as something unusual was Karen Meech at the University of Hawaii, and she knew immediately there was no time to be careful. Within a single week, she had rallied telescopes on 4 continents, calling in favors, bumping other observations, because Oumuamua was already fading and there would be no second appointment. Every image anyone has of this object was captured inside that narrow, frantic window. What came back from that scramble was strange on its own terms. Oumuamua's brightness flickered by a factor of 10 every few hours as it tumbled end over end through the dark. To produce a light curve that extreme, the object has to be wildly elongated, maybe 10 times longer than it is wide. Picture something roughly the length of a football field, shaped less like a boulder and more like a cigar, or maybe flatter still, like a spinning pancake. Comets have tails that is close to their whole identity, ice warmed by sunlight, venting gas and dust into a glowing streak that can stretch for millions of miles. Oumuamua had none of it. No coma, no tail, nothing streaming off its surface as it swung past the sun. Whatever this thing was made of, it was not behaving like any of the icy wanderers already cataloged in our own backyard. Then its path did something it was not supposed to do. As Oumuamua left, astronomers clocked it accelerating slightly faster than gravity alone could account for. The same subtle push you would expect from a comet venting gas as it warms. Except there was no gas, no dust, no tail, no visible outgassing of any kind, and still the object kept speeding up on its way out. Small, measurable, real. Sit with that contradiction for a second because it does not resolve cleanly. A comet-like acceleration from an object with no comet-like tail. A shape unlike anything in the asteroid record. A trajectory that starts and ends outside the solar system entirely. Every explanation anyone offers solves one piece of this and leaves another piece broken, and that gap is exactly where things got interesting. That gap is where Avi Loeb stepped in, chair of astronomy at Harvard, a man with the academic standing to ask an uncomfortable question in a real journal instead of comment section. His proposal, published and peer-reviewed rather than whispered, was that the acceleration might be explained by something built. A thin, light sail catching pressure from sunlight the way a sail catches wind, left behind by a civilization we know nothing about. Loeb was careful with his language, calling it a testable hypothesis rather than a conclusion, and the pushback from the wider astronomical community was immediate and pointed. Most working scientists think the artificial explanation is unlikely. But here is the detail worth noticing. Loeb never fully walked it back. Years later, he is still arguing the natural explanations do not close the case, and he is still, technically, correct that they do not. The natural explanations on offer are not bad, exactly. A chunk of solid hydrogen ice, so fragile it could vent invisibly and evaporate away before instruments ever caught it. A fragment of nitrogen ice, the same material frosting parts of Pluto, sheared off some other frozen world in some other system. Both ideas are physically reasonable. Neither one fully accounts for every measurement. That is simply where the evidence stalled out. There will not be a tiebreaker, either. Oumuamua was visible to us for a matter of weeks, already outbound, already fading past the reach of any instrument we had. No mission was ready to fly. Nothing existed that could chase something moving that fast on that little notice. We got one blurred, tumbling glimpse of a visitor from another star system, and then, permanently, it was gone. There's an old irony buried in all this. Decades before Oumuamua existed as anything but hypothetical, Arthur C. Clarke wrote a novel called Rendezvous with Rama about a mysterious cylindrical object tumbling through the solar system, briefly explored, then lost forever before anyone could answer the obvious questions. Nobody who read that book expected to watch its premise play out for real in the actual sky within their own lifetime. For most of human history, one strange, unanswerable visitor would have been the entire story filed away and left there. Except 2 years later, in Crimea, an amateur astronomer named Gennady Borisov, using a telescope he built and ground the mirror for himself, found something else entirely. Another object on a trajectory gravity could not explain. Another visitor from beyond the sun's reach. This one, at least, looked reassuringly familiar. They called it 2I/Borisov, the second confirmed interstellar object, and unlike Oumuamua, it behaved exactly the way a comet is supposed to. It had a coma. It had a tail. It was actively venting carbon monoxide and water ice as it warmed near the sun, glowing faintly green through telescopes around the world. In a strange way, its ordinariness was its own kind of comfort. At least this one made sense. Normal is doing a lot of work in that sentence, though. Borisov is still a fragment of a completely different solar system, formed around a completely different star, flung outward by some gravitational shove nobody on Earth witnessed, then drifting for possibly millions of years before its path happened to cross ours. 2 confirmed interstellar objects, arriving 2 years apart after 0 confirmed sightings in the entire prior history of astronomy. That timing is not a coincidence. Astronomers had actually run these numbers before either object showed up, estimating on statistical grounds that interstellar debris should be drifting through the solar system constantly, as an ordinary background feature of living inside a galaxy full of other stars. What changed in 2017 was not the universe suddenly sending visitors our way. What changed was us. Survey telescopes finally became wide enough and fast enough to catch something moving at the wrong angle for the first time in the history of the species. Which means Oumuamua and Borisov did not begin passing through in 2017. Objects like them have been passing through for as long as there has been a solar system to pass through it all, quietly, unrecorded, invisible to a species that spent its entire existence without the instruments to notice. Run that thought all the way back. An object exactly like Oumuamua could have tumbled past Earth's orbit during the age of the dinosaurs, or during the last ice age, or during the building of the pyramids, and there's no real reason to think anyone or anything on this planet would have ever known. The sky does not keep records. Only our instruments do, and ours only started working properly a few years ago. Every interstellar visitor that crossed our solar system before 2017 is simply gone from the historical record now, permanently, folded into a blind spot that lasted the entire span of human civilization. Not because those objects were rare, because nobody on Earth had the tools to look up at the right moment in the right way and recognize what was actually passing overhead. There's a facility coming online in Chile built specifically to close that blind spot, the Vera Rubin Observatory, scanning the entire visible sky every few nights with a camera roughly the size of a small car. Some projections suggest it could flag a new interstellar object every single year, maybe more. For the first time, we are building eyes wide enough to actually start counting what has always been out there, drifting past us unannounced. So reconsider what the edge of the solar system actually is. Not a wall, not a tidy boundary separating us from everything beyond the sun's reach. It is porous, and it always has been. Material born around other stars has been sliding through our neighborhood for the entire span of Earth's existence. And for nearly all of that time, we simply lack the ability to look up and notice. Which raises an uncomfortable present tense question. Right now, tonight, it is entirely possible that another interstellar object is somewhere inside the solar system, inbound or already leaving, simply because nobody has happened to point the right telescope at the right patch of sky on the right night. That is not paranoia. That is just what the arithmetic says, given how much of the sky still goes unscanned on any given evening. And Oumuamua's question, the one lobe raised and never fully retracted, is still sitting there, unresolved. Not because the artificial explanation is probably right, most working astronomers think it is not. It sits there because the natural explanations still do not close every gap, because the object itself is gone forever, because there will never be a second observation to settle it. Certainty, in this one specific case, is simply not on the table. This is also the moment the story stops being only about planets. Everything covered so far has orbited the sun, bound by its gravity, part of one shared neighborhood. Oumuamua and Borisov answer to nothing here. They belong to no star in particular. They are debris of the galaxy itself, and their presence in our sky means the story just widened permanently from planetary to interstellar. Consider the scale of it. If our solar system alone has been visited twice within 2 years, the moment we finally had instruments capable of checking, then multiply that by every star system across the galaxy, each one presumably flinging its own debris outward the same way ours does. The number of interstellar wanderers currently drifting through the Milky Way is almost certainly staggering, and nearly all of it will pass by every star in this galaxy completely unseen. The sun does not need to explode to end this. No flare required, no coronal mass ejection, nothing sudden at all. All it has to do is keep doing exactly what it has been doing since it first ignited 4.6 billion years ago, quietly getting brighter on a schedule that was fixed before Earth had even finished forming, and there is nothing anyone can do to renegotiate the terms. Every star that fuses hydrogen in its core brightens with time, and the sun is no exception. As hydrogen converts into helium, the core slowly contracts and heats, and the fusion rate creeps upward year after year, in a process too gradual for any human lifetime to register directly. Today, right now, the sun is already roughly 30% brighter than it was when life first appeared on Earth. It is nowhere near finished. That brightening is already dragging the habitable zone, the narrow band of orbits where liquid water can exist, slowly outward, away from Earth. There's a strange irony sitting inside that fact. As Earth cooks, Mars, of all places, is projected to spend a stretch of time warmer than it has been in billions of years, right as the one planet that actually needs the warmth is losing everything to too much of it. Run the clock forward about 1 billion years, and 1 billion is not an exaggeration, and the sun's output climbs enough to push Earth's climate past a point of no return. The oceans do not freeze. They boil. Water vapor, itself a potent greenhouse gas, traps even more heat, feeding a loop with no brake pedal, a process scientists call a runaway greenhouse. Earth already has a neighbor that finished this exact process. It is called Venus. Astronomers Robert Conan Smith and Klaus-Peter Schroeder ran the actual physics on this back in 2008, tracking the sun's luminosity forward year by year until Earth's oceans fully evaporate. Their number kept landing in the same place, somewhere close to 1 billion years from now. Not a guess, a calculation checked and rechecked, sitting quietly in the scientific literature, mostly unread outside it. That is the deadline almost nobody talks about, and maybe that is because there is nothing cinematic about it. No asteroid, no supervolcano, no single dramatic morning when everything changes. Just sunlight, doing precisely what sunlight does, a fraction more intense every year, for so many years that oceans which took billions of years to fill simply have nowhere left to go but up, into the sky, and out. And here is the detail that makes it worse. This deadline falls roughly 4 billion years before the sun even reaches the dramatic part of its own story. Whatever, if anything, still exists on Earth by then will already be living or trying to on a scorched and waterless rock, orbiting a star that from any distance still looks completely calm, still looks exactly like it does tonight. Eventually, roughly 5 billion years from now, the sun finally runs out of hydrogen fuel in its core. The core contracts under its own weight, heats further, and ignites a shell of hydrogen fusion wrapped around a helium heart that has gone quiet. That shell burns hotter and more efficiently than anything the sun has done before, and it forces the outer layers to expand outward. Dramatically, this is the opening act of the red giant phase. The sun does not swell gently. Models put the final size somewhere between 100 and 200 times its current diameter, engulfing Mercury outright. Then Venus, two planets that have held their orbits faithfully for billions of years, simply gone, absorbed in what is, on a stellar timescale, a remarkably fast sequence. The steady yellow disk that has hung over every sunrise in human history becomes a bloated, dim, reddish sphere large enough to swallow Venus's old orbit hole. Earth's fate at that exact moment is genuinely, seriously contested among astrophysicists, and somehow that uncertainty feels worse than a clean answer would. Some models show the sun's outer atmosphere reaching just far enough to physically engulf Earth, vaporizing it into the outflowing wind. Other models factor in the sun losing mass as it swells, loosening its gravitational grip enough to let Earth drift slightly farther out, surviving as a scorched, airless cinder instead. Surviving is a generous word for either outcome. Either way, nothing about the Earth anyone alive today would recognize makes it through this. Whether it is vaporized completely or merely stripped down to bare, cracked rock drifting inside a red giant's outer atmosphere, the version of this planet with oceans, with weather, with anything alive on its surface, ended long before this particular stage even begins. The red giant phase is not really the extinction. It is the funeral held billions of years after the actual death. Before the sun even finishes expanding, its contracting core crosses a threshold, somewhere near 100 million degrees, and helium itself ignites. Astronomers call this the helium flash, and for a star the sun size, it happens almost instantly, a sudden, self-limiting eruption of fusion inside a dense, compressed core. It does not tear the sun apart. It rearranges it, settling into a calmer stretch of burning helium into carbon and oxygen, a brief, uneasy stability before the swelling resumes. That stability does not last. In its next phase, called the asymptotic giant branch, the sun swells again, further than before, shuddering through a series of unstable thermal pulses as it burns through its remaining fuel in fits and starts. With each pulse, it sheds more of its own outer material into space, layer after layer, peeling itself apart from the outside in, right up until there's almost nothing left of the original star but its core. What eventually drifts away is the most beautiful part of this entire ending. The sun's outer layers expand into space as a glowing shell of gas and dust, lit from within by the exposed, blistering core at its center. Astronomers call structures like this planetary nebulae, and they are, without irony, some of the most photographed, most strikingly colorful objects in the night sky. The sun's own death, from a safe enough distance, would look genuinely gorgeous. Nobody will be here to see it. What is left behind, once the glowing shell disperses into the interstellar dark, is the sun's naked core. Roughly Earth-sized, but packed with something close to half the sun's original mass, held up against total collapse only by the strange quantum pressure of tightly packed electrons refusing to be crushed any further. This object is called a white dwarf, and it will never fuse anything again. There is no fuel left to give a reason to. A white dwarf does not go out quickly. It simply radiates away the heat it already has slowly, almost unimaginably slowly, cooling over a timescale that stops meaning much to a human brain somewhere around the word trillion. Picture it sitting there, small, dense, and dim, right where the sun used to be, in the exact center of what used to be our solar system, doing nothing at all except very, very gradually going cold. Astronomers reserve a name for what a white dwarf eventually becomes. Once it finally, completely cools, a black dwarf, dark, inert, radiating essentially nothing. Here is the strange part. Not one has ever actually formed anywhere in the observable universe. The universe itself is only 13.8 billion years old, and that is nowhere near enough time for even the oldest white dwarfs already out there to finish cooling all the way down. Sit with that for a second, because it is genuinely strange. The sun's true, final, cold, and lightless ending is a stage of existence that has never once occurred to any star anywhere in the entire history of the universe so far. We're not describing something that has already happened somewhere else. We are describing a destination so distant in time that literally nothing has arrived there yet. And our sun is on that road already, has been since the moment it lit. Go back to where this film actually began, to the summer of 1859, to a telegraph operator watching sparks leap off his own equipment, while the sky over the equator turned red with aurora that should never have been visible that far south. That was the sun too. Restless, unpredictable, throwing a burst of charged particles at Earth with enough force to threaten the electrical grid of an entire planet, a century before that grid even existed. Two very different threats, both entirely true at once. The Carrington event was a warning about how violent the sun can be on a random Tuesday. No schedule, no notice, a magnetic tantrum aimed at whatever planet happened to be standing in the way. Everything covered in this chapter is the opposite. No violence required anywhere in it. No accident, no bad luck, no villain in the story at all. Just the slow, patient, thermonuclear arithmetic of a star doing precisely what stars its size are built to do. And that might be the more unsettling version of the two, honestly. A solar storm is at least a threat you can imagine defending against. A hardened grid, better satellites, more warning time, some kind of plan. Stellar evolution does not negotiate. It does not care what defenses anyone builds. It is not an event so much as a countdown that started before Earth existed and will finish precisely on schedule, whether or not anyone is left to notice it happening. Every ocean, every ice sheet, every single living thing on this planet right now is operating on a lease that already has an end date printed on it, set long before any of us arrived, non-negotiable, filed away in the physics of an ordinary star quietly doing its job. That is not a threat. It is simply the paperwork nobody reads. There is at least one wild proposal on record. In 2001, astronomers Don Koryansky, Gregory Laughlin, and Fred Adams calculated that repeated close passes by a large asteroid, redirected again and again over billions of years, could theoretically tug Earth's orbit gradually outward, staying just ahead of the sun's expansion. It would take thousands of precisely engineered flybys, spaced across roughly 6 billion years, executed without a single serious mistake by a civilization that does not exist yet. Call it a plan. Call it wishful thinking with equations attached. So the sun's own ending, when it finally comes, is quiet. No explosion, no final flash, just an ember cooling in the dark for longer than any number can really mean to a human mind. But not every star gets a retirement that gentle. A star can die so violently that the radiation from its death can sterilize the surface of a planet orbiting a completely different star, light years away, with absolutely no warning beforehand. No warning, because the light announcing the danger and the danger itself travel at exactly the same speed. By the time you can see it happening, it has already arrived. Supernovae and gamma-ray bursts sit at the very top of the universe's violence scale, among the most energetic events that have happened since the Big Bang itself. For a period of days, a single dying star can outshine every other star in its entire host galaxy combined. Billions of them, briefly reduced to background noise next to one point of light. Here is how an ordinary massive star actually dies. Deep in its core, it spends its life fusing lighter elements into heavier ones, releasing energy at every step, all the way up the periodic table. That process works right up until the core is made of iron. Iron fusion does not release energy, it consumes it, and the moment a star's core turns to iron, The entire engine that has held it up against gravity for millions of years simply switches off. What follows takes about 1 second. The iron core, suddenly unsupported, collapses in on itself at a meaningful fraction of the speed of light, crushing down until it rebounds off its own density and slams back outward as a shock wave powerful enough to blow the rest of the star apart. That is a supernova, not a slow burn, not a fade out. A structure that took millions of years to build, unmade in about the time it takes to say the word. Gamma-ray bursts are the more extreme cousin of that event, and they remain the most energetic explosions confirmed anywhere in the observable universe since its beginning. Instead of radiating outward in every direction, a gamma-ray burst focuses its energy into two narrow, relativistic jets, blasting out from the poles of the collapsing star like a lighthouse beam built from pure gamma radiation. Get directly in that beam's path, and distance stops being much protection at all. Some gamma-ray bursts come from a massive star collapsing, the same basic mechanism as a supernova, just with the jets forming as the core caves into a black hole. Others come from an entirely different scenario, two neutron stars, already unimaginably dense, spiraling into each other and merging in the last fraction of a second of their existence. Different origins, same result. A beam of radiation so intense it barely resembles anything else physics produces. This is where astrophysicists coined a phrase that sounds almost too blunt for a peer-reviewed paper: the kill radius. It is exactly what it sounds like, a calculated distance from Earth within which a nearby stellar death could strip away the ozone layer, flood the surface with unfiltered ultraviolet radiation, and collapse the base of the food chain before most species even understood what was happening to them. For an ordinary supernova, current estimates put that kill radius somewhere between 25 and 50 light years. Inside that range, the gamma radiation and cosmic rays from the explosion would be strong enough to break down atmospheric ozone across a meaningful fraction of the planet, letting in enough ultraviolet light to damage the DNA of anything living near the surface, on land, or in shallow water, essentially everywhere the sun actually reaches. A gamma-ray burst changes the math entirely, because a burst does not need to be close. It needs to be aimed correctly. A gamma-ray burst pointed directly at Earth could theoretically inflict comparable damage from thousands of light years away, an entire galaxy's width of distance rendered almost irrelevant by how tightly focused the beam is. The only genuine mercy in that scenario is how narrow those beams are and how astronomically unlikely it is for one to line up with us at all. Some scientists suspect this has already happened once. Around 445 million years ago, Earth suffered the Ordovician extinction, wiping out something close to 85% of marine species, concentrated overwhelmingly among organisms living in shallow, sunlit water. That pattern, sudden and worse near the surface, is exactly what a burst of ultraviolet radiation following a nearby gamma-ray burst would produce. Nobody can prove it, but the fit is uncomfortably good, and the hypothesis has never fully gone away. The reassuring part, and there is one, is that nothing currently known to astronomers sits inside Earth's actual kill radius. Every candidate close enough to matter has been checked, tracked, and ruled distant enough for now. But one star in particular sits close enough and behaves strangely enough that astronomers keep an almost obsessive watch on it anyway, not because it threatens us, but because of what it is about to become. That star is Betelgeuse, the bright reddish point marking the shoulder of Orion, visible with the naked eye from nearly anywhere on Earth. It is a red supergiant, one of the largest stars known, so vast that if it replaced the Sun, its outer surface would reach somewhere past the orbit of Jupiter. Its exact distance from Earth is still debated, somewhere around 500 to 700 light years, and even that uncertainty tells you something about how strange this star actually is. In late 2019 and into early 2020, Betelgeuse dimmed dramatically, losing roughly 2/3 of its normal brightness in a matter of weeks. visibly different to anyone who simply looked up. Astronomers scrambled. Amateur observers speculated the star might be about to go supernova in real time, live in front of the entire species. It made international headlines. For a few unnerving months, a genuinely large number of people were quietly wondering if they were about to watch a star die with their own eyes. The actual explanation turned out to be a colossal cloud of dust, a chunk of the star's own outer surface, ejected and cooling in front of it, blocking the light rather than the star itself failing. Betelgeuse is still there, still burning, and current estimates give it anywhere from the next few thousand years to the next 100,000 years before it actually goes. In stellar terms, that is soon. In human terms, nobody alive will see it. And even then, at 500+ light years away, it sits safely outside the kill radius. Betelgeuse will be a spectacle, not a threat. Whatever a star like Betelgeuse leaves behind depends entirely on how much mass survives the explosion itself. Below a certain threshold, the crushed core stabilizes into something almost too dense to describe honestly without sounding invented. Above that threshold, gravity does not stop at all, and the result is something physics can barely finish describing. Both outcomes are sitting in the night sky right now, scattered across the galaxy, remnants of stars that finished this exact process long before humans existed to watch. The lighter outcome is called a neutron star, and it is, without exaggeration, one of the strangest stable objects known to exist. Take a star with more mass than the Sun and crush it down to a sphere roughly 12 miles across, about the width of a city. That is a neutron star. The atoms inside are not really atoms anymore. Gravity has crushed the space out of them entirely, packing protons and electrons together into neutrons until there is nothing left to compress. Try to picture the density involved, because the number alone does not land. A single teaspoon of neutron star material would weigh somewhere around 1 billion tons here on Earth, roughly the mass of a mountain, compressed into a spoon. Objects that dense bend the physics happening near them, warping space itself measurably, all while spinning, in some cases hundreds of times every single second. Some neutron stars sweep a beam of radiation around as they spin, the way a lighthouse sweeps its light across dark water. And if Earth happens to sit in that beam's path, we detect a pulse of radiation with a regularity so precise that the first ones discovered were briefly nicknamed little green men. Before astronomers accepted, they were simply looking at the most accurate natural clocks in the universe. These are pulsars, and some of them are more reliable timekeepers than anything humans have built. A smaller number of neutron stars take this even further. Magnetars carry magnetic fields trillions of times stronger than anything producible on Earth. Fields powerful enough that, from a few thousand miles away, they could theoretically distort the atoms in a human body simply by being nearby. One magnetar flare detected in 2004, from a source roughly 50,000 light-years away, briefly outshined the full moon in gamma rays and measurably disturbed Earth's upper atmosphere. From 50,000 light-years away. Cross a certain mass threshold in the collapsing core, and even neutron degeneracy, the same quantum resistance that holds a neutron star up, is not enough. Gravity simply wins outright, with nothing left in physics capable of stopping the collapse. What forms instead is a black hole, and calling it an object almost undersells what it actually is. It is a region of space where gravity has become so absolute that nothing, not light, not radiation, not information of any kind, can climb back out once it crosses inside. The boundary marking that point of no return is called the event horizon, and it is worth being precise about what it is not. It is not a surface. There is nothing solid there to hit, nothing to see, no wall. It is simply the distance at which escape stops being mathematically possible, a line drawn by gravity itself, rather than by any material thing, and crossing it changes absolutely nothing about how it looks, right up until it changes everything about what happens next. Fall toward a black hole, and gravity does not treat every part you equally. The pull on whatever reaches the black hole first is measurably stronger than the pull on whatever trails behind it, and that difference stretches you, slowly at first, then catastrophically, into a thin, elongated stream. Astrophysicists actually call this spaghettification, a genuinely silly word for a process that ends with every atom of you separated from every other atom, strung out across space in a line. At the very center of it all sits the singularity, and this is the point where honesty requires admitting something uncomfortable. Nobody actually knows what is there. The equations of general relativity, which correctly describe essentially everything else in this film, simply stop producing meaningful answers at that point, predicting infinite density in infinitely small space. That breakdown may be the literal edge of what physics, as currently understood, is even capable of describing. So with everything this chapter just walked through, because this is the darkest point in the entire story. A star can die and end life on a world it never touched. Orbiting a sun it has no relationship to, light years away, with no warning possible because the warning and the danger arrive together. Violence at this scale does not require proximity. It does not require malice or aim or intent of any kind. It only requires mass, time, and physics doing exactly what physics always does. For now, Earth sits outside every kill radius anyone has calculated, comfortably distant from Betelgeuse, from every known magnetar, from every plausible gamma ray burst source close enough to matter. That is genuinely, currently true. But it is worth noticing that comfort here is really just a measurement. A distance on a chart, not a promise, not a guarantee, just the current answer to a question the universe never agreed to keep answering the same way forever. Somewhere between 100 and 400 billion stars are burning in the Milky Way right now, and depending on which count you trust, that number might be low. Run the math on how many of those stars have planets. How many of those planets sit in the narrow band where liquid water could exist, and you get a figure so large it stops feeling like a number and starts feeling like a certainty. And yet, as far as anyone has ever proven, exactly one of those worlds has someone standing on it, looking up, asking the same question you're about to ask. Astronomers call it the Drake equation, a formula built in 1961 by Frank Drake to estimate how many communicating civilizations might share this galaxy with us. Plug in the number of stars, the fraction with planets, the fraction of those planets that could support life, the fraction where life actually starts. Even using cautious, conservative numbers, the equation tends to spit out thousands. Optimistic ones push it into the millions. Nobody serious argues the galaxy should be empty. The argument is over how full it should feel. We're not guessing blind anymore either. Telescopes have confirmed more than 5,000 exoplanets since the 1990s, and a real, growing subset of them sit inside their star's habitable zone, the region where a planet's surface could plausibly hold liquid water. TRAPPIST-1, a small red dwarf 40 light-years from here, has 7 rocky planets, 3 of them in that zone, orbiting so close together that from the surface of one, you could watch the others cross the sky like moons. None of this is fringe science anymore. It's cataloged, peer-reviewed, sitting in public databases anyone can search. Sun-like stars, check. Rocky planets at the right distance, check. The raw chemical ingredients for life, scattered through interstellar clouds and confirmed in meteorites, check. Every box the universe needed to tick to make company for us. It has apparently ticked over and over billions of times for billions of years before we even showed up. In the summer of 1950, the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos, the same lab that had built the atomic bomb 5 years earlier. The conversation drifted, as lunch conversations do, to flying saucers and the possibility of life among the stars. And then Fermi, almost offhand, asked the question that would outlive every physicist at that table. Where's everybody? He wasn't being dismissive. Fermi did the arithmetic right there, napkin style, and it bothered him. Even a civilization crawling along at a fraction of the speed of light, using nothing more exotic than slow interstellar probes, could cross the entire Milky Way in something like 5 to 50 million years. That sounds vast until you remember the galaxy is roughly 13 billion years old. Even one early civilization should have had time to fill it, colonize it, leave fingerprints on it, many times over. This is the part that actually unsettles the people who study it. You don't need warp drives or wormholes for the math to work. A self-replicating probe, something that arrives at a new star system, mines a moon or an asteroid for raw material, and builds copies of itself to send onward, would spread exponentially. Physicists have modeled it. Give that kind of technology just a few million years, a blink of geological time, and it should have reached every star in this galaxy already, including ours. So where are the probes? Where are the radio signals, the megastructures, the waste heat of some ancient engineering project leaking into the infrared? We have pointed instruments to the sky for over 60 years now, listening across a huge range of frequencies, watching for anything that looks unnatural, artificial, deliberate. And across all of it, every survey, every all-sky scan, we have found precisely nothing that anyone can confirm. Just noise, just stars doing what stars do in total silence. Strip away the illustrations and look at the real data, and the Milky Way is mostly dark. The light from every one of those billions of stars is scattered across a disk about 100,000 light-years wide, and between each point of light sits a gulf of cold, silent space that swallows the imagination. We picture the galaxy as crowded. It isn't. It's mostly distance, vast and indifferent, and that distance is what turns an ordinary silence into something that feels deliberate. In 1996, an economist and physicist named Robin Hanson gave this unease a name. He called it the Great Filter, some barrier so severe that it stops almost every planet story before it can produce a civilization capable of being noticed by another. Somewhere between lifeless rock and a species broadcasting into the void, something filters almost everyone out. Nobody knows whether humanity is looking at that filter in the rearview mirror already behind us, or still driving straight toward it. That uncertainty alone is enough to keep working scientists awake at night. One version of hope says the filter sits behind us, far behind, back at the very start. Maybe the leap from simple chemistry to the first self-copying molecule is so staggeringly improbable that it has happened, as far as we can tell, exactly once in the observable universe, right here, roughly 3.7 billion years ago. If that's true, we are not the survivors of a cosmic gauntlet. We're the anomaly, the one time the dice actually landed right. Or maybe it's further along than that. For roughly 2 billion years, life on Earth was nothing but single cells, floating, dividing, going nowhere in particular. The jump to complex cells with nuclei, the ancestors of every plant, animal, and fungus alive today, happened just once in one lucky merger between two microorganisms. Multicellular life took another billion years after that. Each step is a doorway that, for all we know, most worlds never walk through. The other version of the filter is not comforting at all. It says the hard part isn't behind us, it's still ahead, waiting somewhere between where we are now and where a civilization would need to be to leave a visible mark on the galaxy. Maybe intelligence, every time it evolves anywhere, eventually builds the tools sophisticated enough to end itself. And maybe it always does. Every single time, before it ever gets the chance to say hello. We built our own candidates for that filter within 1 century of discovering radio waves. Nuclear weapons capable of ending civilization in an afternoon, arriving in 1945. A climate we are actively destabilizing through our own combustion. And now, artificial intelligence systems whose long-term behavior even their own creators cannot fully predict or control. Maybe every intelligent species reaches this exact narrow window, technological enough to reach the stars, technological enough to destroy itself first, and maybe almost none of them make it through. Notice that neither version of this story is good news, not really. If the filter is behind us, we're freakishly, almost impossibly rare, alone by default, with no one coming and nowhere to send a signal that anyone will ever receive. If the filter is ahead of us, then every civilization that has ever risen anywhere in this galaxy, ours included, is currently walking towards some kind of door that does not open. Pick your poison. Nobody has found a version of this equation where we simply relax. People have been listening for an answer since 1960, when the astronomer Frank Drake pointed a radio telescope in Green Bank, West Virginia, at two nearby stars and called it Project Ozma. It found nothing. The search never really stopped after that, just grew, spreading across observatories on every continent, scanning millions of frequencies for anything that looked less like a pulsar and more like a sentence. In August 1977, an Ohio State University telescope nicknamed Big Ear picked up a burst of radio noise so strong and so precisely matched to what scientists expected an artificial signal to look like that the astronomer reviewing the printout circled it in red pen and wrote a single word in the margin. Wow, it lasted 72 seconds. It has never repeated, never been explained, and never come again, not in over 45 years of watching that exact patch of sky. That is the closest thing to a maybe that anyone has ever recorded. One unexplained signal, printed on a strip of paper, in almost 65 years of organized listening. Every other survey across every other patch of sky has returned the same result. Static, background noise. The hiss of a universe that, if anyone else is out there, has not said a word to us, not once, not by accident, not on purpose. Scientists have floated other explanations, some more comforting than others. The zoo hypothesis suggests advanced civilizations are watching us deliberately, in silence, the way we'd observe an ecosystem without disturbing it. The dark forest hypothesis goes the opposite direction entirely, arguing that every civilization stays quiet on purpose because broadcasting your location to the universe might be the last mistake you ever make. And the rare Earth hypothesis simply says our specific mix of ingredients, a large moon, a stable orbit, plate tectonics, a Jupiter-sized bodyguard sweeping up debris, might just be freakishly unusual. Here is what nobody can honestly tell you, no matter how many papers get published or how many telescopes get built. We do not know which story is true. We do not know if the silence means we are early, rare, hidden, or simply doomed on a schedule nobody has handed us yet. Every explanation fits the same data equally well, which is another way of saying we have almost no data at all. Step outside tonight, somewhere dark enough to actually see it, and look up. Every star in that sky is a candidate. Every one of them might have its own version of Earth, its own ocean, its own history, its own species wondering the exact same thing you are right now. Or every single one of them might be exactly what it looks like. Empty rock, orbiting fire, going nowhere, forever, with no one home to notice. And there is a colder thought sitting underneath all of this, one most people don't like to say out loud. Whatever answer the universe is hiding, humanity itself is a live experiment currently in progress. We have already survived nuclear weapons for over 80 years. We have not yet finished the climate test or the artificial intelligence test or whatever test comes after those. We are right now walking directly through the exact window this chapter has been describing. So if you want to know whether the great filter sits behind our species or somewhere just ahead of it, in the next century, the next 1,000 years, there's only one honest answer anyone can give you. Nobody knows. Not yet. Maybe not ever. And that not knowing is about to matter more than you think, because the next place this story is going to look isn't out there among the other stars at all. It's up at the sky itself and at what it's actually showing you every single night. Go outside tonight, find a patch of sky dark enough to actually see it, and look up. Some of the light hitting your eyes right now left its source before you were born. Some of it left before your parents were born. And a small amount of it, if you know where to look, came from a star that may not even be there anymore, the light still traveling long after the fire that made it went out. Light is fast, But it isn't instant, and the universe is so large that the difference between fast and instant becomes the whole story. Light crosses the gap between Earth and the Moon in about 1.3 seconds. It takes about 8 minutes to reach us from the Sun, which means the Sun you picture as blazing away right now is 8 minutes old information. Even our own star, the one keeping us alive, we only ever see in the past tense. Push the distance out further, and the delay stops being trivial and starts being strange. Sirius, the brightest star in the night sky, sits about 8.6 light years away. So what you're seeing left in the year that fits 8.6 years before tonight. Proxima Centauri, the nearest star to our Sun, is 4.2 light years out, close enough by galactic standards to feel like a neighbor, and still too far to say anything to in a single human lifetime and get an answer back. Betelgeuse, the red giant shoulder of Orion, sits roughly 548 light years away, and we talked in an earlier chapter about how a star like that dies, violently, all at once. Here is the part that should genuinely bother you. If Betelgeuse exploded tomorrow, its actual tomorrow, we would not know for over 5 centuries. It could already be gone. It could have been gone since before Shakespeare was born, and we would still be standing out here tonight, watching it shine like nothing happened. Now go further still. The Andromeda Galaxy, the most distant object you can see with the naked eye on a clear night, sits about 2.5 million light years from Earth. The light landing in your eyes tonight left Andromeda when the earliest members of our own genus were just learning to walk upright on the African savanna. You're looking at a photograph of the deep past every single time you glance up, whether you meant to or not. Here's the part that gets genuinely disorienting once you sit with it. Every star in the sky is a different distance, which means every star is a different age of light, all of it arriving in your eyes at the exact same instant. The night sky isn't one snapshot of one moment. It's a patchwork, stitched together from thousands of different points in time, layered on top of each other like transparencies, none of them showing you the same now. Technically, this is true of everything you have ever seen. Light takes time to travel from any object to your eye, even across a room. But a human scale, that delay is so small it might as well not exist. The sky is where that small, ignorable lag stops being ignorable and turns into centuries, into millennia, in a spans of time longer than our entire species has existed. Distance is what turns a rounding error into an abyss. We spent an earlier chapter on what eventually happens to our own Sunday. In roughly 5 billion years, it swells into a red giant, swallowing Mercury, Venus, quite possibly Earth itself, before collapsing down into a slowly cooling white dwarf. Nobody needs to lose sleep over that on a human timescale, but it is locked in a certainty sitting on a cosmic calendar, and it means every conversation about the future of this planet has a hard, final deadline stamped somewhere in the fine print. Set that deadline next to the silence we sat with in the last chapter, the hundreds of billions of stars, the odds that should be producing neighbors, the answer that has never come. If contact ever happens, if some signal ever does arrive confirming we're not alone out here, there is no reason to assume it happens on a timeline that's convenient for us. It could take another 100 years. It could take 100,000. It could take longer than our species has left to listen for it. That is the quiet, uncomfortable joint where these two ideas meet. The stars we're looking for answers from are so far away that even good news would arrive late, decades or centuries after whoever sent it is already gone, decades or centuries, possibly after whoever receives it is gone too. We may be alone in space and alone in time both, reaching toward people or the absence of people we will never get to meet. On February 14th, 1990, the Voyager 1 spacecraft was 3.7 billion miles from Earth, well past the orbit of Neptune, on its way out of the solar system for good. At the request of the astronomer Carl Sagan, NASA turned its camera around, back toward home, and took one last photograph before the instrument was powered down to save what little energy remained. Nobody expected the picture to show much. It didn't. That was the entire point. In that photograph, Earth is a single pixel, less than the width of a grain of sand held at arm's length, caught inside a stray band of scattered sunlight that happened to be passing through the camera's lens at that exact angle. You would not find it if you didn't already know exactly where to look. Every person who has ever lived is somewhere inside that pixel. There is no second pixel standing by to confirm any of it. No wide shot, no establishing frame. Just that one tiny washed-out point of light. Sagan wrote about that image for years afterward, and the line people remember is the one about a mote of dust suspended in a sunbeam. But the part worth sitting with is what he said came bundled with it. Every king and peasant, every triumph and tragedy, every war fought over some momentary advantage. All of it happened on that pixel. Not beside it, not near it, on it. The entire scale of human history fits inside a smudge of light you'd wipe off a camera lens without a second thought. Every terror this film has walked you through, the sun that will eventually swallow its own planets, the stars that die by exploding outward or collapsing into black holes that erase light itself, the gamma ray burst that could sterilize a hemisphere from across the galaxy, all of it is scaled against that one single pixel. The universe was never being cruel to us, specifically. It doesn't know we're here. It has never once had to notice something this small. And there's a strange twist folded inside all of that indifference. Every atom of calcium in your bones, every atom of iron in your blood, every atom of oxygen in the breath you just took was forged inside a star that had to die to release it. You're watching this story from the outside, and you're also made out of the wreckage of earlier chapters. The universe built the dangers we spent 18 chapters describing. It built you out of the exact same material. That is not a comforting fact dressed up to sound poetic. It's simply true, verifiable, checked against the periodic table. The calcium came from supernova. The iron came from supernova. You have been carrying pieces of dead stars around with you this entire time, in your teeth, in your blood, without ever being asked whether you wanted the job. So think again about what you're actually doing the next time you look up at night. You're not looking at the universe as it is. You cannot. Nobody can. You're looking at an enormous, overlapping stack of different pasts, arranged to look like a single present, and there's no way to see it any other way. Not with better telescopes. Not with more time. The delay isn't a limitation of our instruments. It's a fact about how light and distance work, one that no future technology will ever repair. There may not even be a meaningful answer to the question of what the universe looks like right now, this second, everywhere at once. Because right now depends on where you're standing, and everywhere you could stand is a different number of years removed from everywhere else. The universe doesn't have a single present tense. It has billions of them, each one running on its own private delay, and we are only ever handed the one closest to us. Which makes the silence from the last chapter even stranger to sit with. If another civilization is out there right now, and whatever right now means for them, we would have no way to know except by watching light that already left them behind, possibly centuries ago, possibly from a version of their world that no longer exists in the way that light describes it. It's possible we are failing to hear a voice for a much stranger reason. We might be listening for an echo of a room that emptied out a long time ago. There's a phrase some astronomers use, half joking, that the night sky is a graveyard lit up to look like a party. It's not entirely fair. Plenty of what you see up there is still burning, still exactly where the light says it is. But you can never know, from where you're standing, which lights are which. Every star could be current. Every star could be a memorial. The sky keeps that secret from you on purpose, or at least it feels that way. None of this resolves the question the last chapter left open, whether the silence out there means we're early, rare, hidden, or simply running out the clock on a filter we haven't hit yet. It doesn't resolve anything. What it does is change the shape of the question, because now you have to ask it while accepting that any answer, if it ever comes, arrives on a delay measured in centuries at best, and on a delay measured in something closer to forever at worst. So this is where the film leaves you, standing outside, under a sky that has never once shown you the present moment, Not one single time in your entire life. Every answer about whether we're alone might already be sitting in the light, traveling toward Earth this very second, decades or centuries from arriving, aimed at a version of this planet that won't look anything like the one you're standing on right now. It might already be too late to matter to you personally. It might arrive long after everyone who ever watched this film is gone. Somewhere above you tonight, a star is quietly dying, and you cannot tell which one. Somewhere above you, a star is quietly being born, and you cannot tell which one of those either. The sky keeps no schedule you're allowed to read. It only ever hands you the light, long after the truth of it has already moved on without you, and asks you to call that watching the stars.